yesterday. This first portion of the day, as always, is go over stuff before. And we are here to help. Are we able to use the tools introduced, such as TopSap, continuously after this course without connecting to OpenSAR Lab? Well, if you install ICE on your own machine, then TopSap is one of the standard scripts for processing that is installed with it. So yes, and we will also provide the Docker container information, the Docker file you need to actually install the whole environment that we've been using in OpenSAR Lab locally on your machine as well. So you'll be able to use the notebooks in that case as well.
Yeah, the TopSap notebook is a way to explain how TopSap the TopSap works, but the actual TopSap doesn't require all the Jupyter Lab interface. You can just run that. It's really running from the command line. The TopSap notebook is just calling the command line version of topsap.py to do the steps. So if you don't want to install the whole Docker container and the Jupyter Lab, and you can just install ICE on your local computer and run TopSap separately without, if you don't want to install all the other Jupyter Notebook, Jupyter Lab interface.
And I think Eric mentioned the last time when we were going through this that you can actually run it in one go. You don't have to run it step by step like we were doing. You just say,
yes, yeah, that's very important. Normally, I just run all the steps together.
What's with that with the WinSAR license message that pops up when you're running ICE commands?
Yeah, so when ICE was developed originally, almost 15 years ago now, and we had worked JPL and Stanford. And Stanford had written some modules that were used in some of the earlier applications in ICE, and those. I don't know, for whatever reason, when so we got a license set up through WinSAR that people could get the license to use ICE through WinSAR by becoming members of WinSAR. So then you could get that older version of ICE. Then starting in January 2019, almost 3.5 years ago, we made a new open source version of ICE. But I don't know, for whatever reason, Stanford University didn't want to make the parts that they had written open source and put them into the GitHub with the rest of ICE. So we had to strip out all the modules that were written by Stanford, and those were used in these old apps that are now obsolete anyway. So we now use a StripMap app and StripMap stack to do processing of StripMap data. The old apps were called InSAR app and ICE app. So occasionally you'll see those old apps in some of the directories, but some of the lower level modules that are necessary to run those old apps are not in the GitHub version. And if you really want to use those old apps, then you have to get the license from WinSAR.
That
To be
language is
good.
still in there as a holdover from like no one. Someone just
Yeah, it's a holdover from before, from before we did this switch 3.5 years ago. So since January 2019, all the newer versions since January 2019 are only the GitHub version, and those old versions are not being maintained. So I don't know, we really should take those messages out. It's kind of, it's very misleading. People are always asking questions, and
I think
there's people that come and try to use those old apps and they don't work anymore because you know, something changed, and I think it's just misleading.
you get that message, I think, when you import ICE, right? I think that's
Yeah, when you run ICE on the command line, it prints that out at the very first message of running it. I don't. That seems like I didn't set that up. I think I didn't put that in there. I'm not sure.
literally in the Python. If you type import ICE, I think that message comes up when it imports the ICE libraries. So it's like kind of hard bound into like the very deep recesses of the
Yeah,
ICE.
so it's somewhere we have to. Somebody knows where it is. It is one of the things that's difficult about the ICE software is it has a very complicated structure to the software. There's lots and lots of different parts that are sort of pulled in different ways, and it's can be really tricky to find things and change them. Like when I had wanted to fix the problem last week we were having with the DEM downloads from the land processes DAC. I had to go and change 6 different files in like 4 different directories, spread in different places within the ICE code. Fortunately, I was able to search for this with grep through all the. No, actually, I used search on my Mac, the Mac Spotlight search, to find that specific string of the USGS server that needed to be changed from HTTP to HTTPS.
I saw that. Eric Menzies managed to write a sed script to do it. Which I tried and it works, which is cool.
That sed script. That's a better way to do it. But
all right, we have another question. Can we compare InSAR and GPS if GPS location is away from InSAR deformation zone? I mean, it's hard to compare them if they don't overlap, I would say. I mean, generally speaking, if you have GPS within your InSAR interferogram, that's great, because then you can use it as a reference location. You can actually make, because GPS measures absolute deformation, you could potentially tie your interferogram to it. GPS is more noisy in the vertical, so more uncertain, so that it's not a perfect match with what you get from InSAR often, but it certainly can be useful. But yeah, if they don't overlap, it's very hard to compare them. Not impossible, but usually you would want to make sure that they overlap somewhat. Any other questions? Have another 20 minutes set aside for time. Another question is, do people model landslide related deformation like we did earthquakes? Or is that more the domain of time series? I mean, Eric probably has a lot to say about this. My point would be that earthquakes are elastic failure on faults, and usually that extend to great depth. Landslides are very superficial, and they are not elastic in the way that earthquakes are. So using the same tools that we used yesterday to model earthquakes, to model landslides, would probably be incorrect.
Yes, no, it's not elastic at all. I suppose you could try to model a landslide as a very, very shallow fault that's just 10 meters or 20 or 30 meters below the surface, but I don't think that'll work. You'd have to, it's not just the fault on the bottom, but there's 2 faults on the side. because the landslide is sliding past the sides of the ground surface. So it's really, it's not elastic at all. It's a translation rather than an elastic deformation.
There are these granular models, right, that you can use to represent things like that. Where you can model like a bunch of particles that move. That's much more like what a landslide is. But I haven't used them.
Yes, there's definitely civil engineering landslide models or finite element models. And with a finite element model, you can certainly make an element that's the landslide with a surface between elements that has a friction amount, and then we also can try to what we're trying to understand now is how the friction on the base changes with time and with rainfall. You know, how the water, when it rains on the top, takes some time for the rain to get down to the sliding surface, and then how does that affect the sliding surface? There's a lot of modeling that goes into landslides, but it's not something you could just do with Okada for sure.
There's a simple question here: can we use ICE to do PSI or SBAS? And the answer is no, not directly. You can make the interferograms to do those analyses with ICE, but to do PSI, you need to use a code like stamps. To do SBAS, you should use MintPy. And both of those can accept inputs from the ICE stack processor, which is a set of scripts that use ICE to make a load of co-registered SLCs or co-registered interferograms. We will talk about that on Friday, like how you run these scripts. That's the very last thing we'll talk about in the course.
Yeah, so we have three different stack processors in ICE. There's a strip map stack that's for processing strip map data from a number of satellites. There's a special one called for the ALOS-2 satellite data called ALOS stack, ALOS-2 stack. Postdoc working with me wrote that software, Shunren Liang, and it does strip map. It does both ALOS-2. It does ALOS-2 data processing, either strip map data or ScanSAR data. There's a lot of ALOS-2 ScanSAR data that's going to be JAXA is going to release publicly at the ASF in the next year or so. And it's the ALOS stack processor does the stack processing for the ALOS-2 data, and then there's top stack for the Sentinel-1 TOPS data. So there's three different stack processors depending on what type of data you want to process.
Next question is, how can we co-register different SLC products instead of making a stack for InSAR? I'm referring to using fine co-registered SLC products polyometric studies. Well, in the stack processors, you have several options about how far you take the stack and what you do with it. You can choose just to make an SLC co-registered stack and then stop at that point if you want to. So that might be what you want to do. That's your proposed application. You can also make the interferograms if you want to, and combinations of SLCs, different pairs of SLCs to make interferograms. There are various adjustable parameters that choose how many interferograms you make. And you can also make dense offset maps, which we'll talk about a bit later today. I think Forrest is going to present on that, how you use Autorift to do pixel tracking, so dense offset mapping, and you can also make stacks of those. So these are
the stack processors we have now are really designed for interferometry, so they only process a single channel of a polarization at a time. But you could run it if you have dual polarization data. You can run the stack processor twice, once for the HH polarization and one's for HV, if those are the two polarizations you have, or if you have fully full quad pole polarizations, then you could run it 4 times. It's a little bit cumbersome because we didn't really design it for polarimetric studies. But one of the things that that is available is that there is UAV SAR data, SLC stacks, where the SLCs and the UAV SAR stacks are already pre-processed by the UAV SAR team, and they're co-registered, and some of them are fully polarimetric. Most of them are only a single polarization because the investigator that asked for that stack was only interested in interferometry and not in polarimetry, but there are a few polarimetric UAV SAR stacks.
And the other thing to note is that when you do the stack registration, it registers to the topography. I mean, that's the topo step that it runs right at the beginning. So the stacks should be, they should be co-registered appropriately to that. They should be directly comparable. Use the same reference.
Yes.
Same reference date. What's the difference between MintPy and stamps? Well, they are made by different people. Stamps is a much older code. It runs in MATLAB. It does persistent scatter processing. It also does SBAS, and it tries to combine them into one glorious combined product. It is very, very resource intensive and very slow. It can give amazingly good results, but it also takes a long time. And really, I think it has been superseded by this code that Haresh was talking about yesterday, Fringe, which is not quite mature enough yet that we're feel ready to teach it to people. MintPy, on the other hand, is something which is very flexible and very fast. It's an SBAS code, only does SBAS, and it works well enough and fast enough that you can get pretty good results in a matter of 10, 15, 20 minutes, rather than several weeks, which is how long it takes to run stamps at high resolution over an area. So yeah, stamp still exists, and it does accept input from ICE stack process into SLCs. There is an interface that's been built between ICE and stamps, but I'm not sure at this point how well maintained it is. That's another reason that we don't really teach it anymore. 5 years ago we did mention it in this class, but these days we've kind of moved on. How accurate is deformation we estimate for a fault in case of multiple aftershocks like Gorka 2015 and aftershocks followed for like a month? One of the aftershocks of the Gorka earthquake, which was the Gorka earthquake, was a magnitude 7.8 earthquake in Nepal, and it was followed by a magnitude 7.3 aftershock like a couple of weeks later. That earthquake, that aftershock, paid a huge deformation signal in its own right, and definitely should be treated as a separate earthquake when you're modeling. Most of the time, if you have earthquakes that have large aftershocks, those aftershocks tend to be significantly smaller than the main shock, and even if that deformation is included in the interferogram, you would never be able to separate it out. Normally, we just assume that the biggest earthquake is the one that we're capturing. I guess there have been a few cases when there have been like earthquakes of similar size that came in quick succession, and we've not been able to have SAR acquisitions between them. So we have to model them kind of together and as a bundle. Or when you've had an earthquake swarm, that's sometimes the case. So yeah, without using information from seismology or something else, sometimes you can't separate out those aftershocks from the main shock. Is it possible to predict earthquakes? No. It still is not possible to predict earthquakes. Anyone who says they can is either being dishonest or deluded. For ICE top stack processing, is it possible to not use a bounding box and process the entire SAR scene? Yes. By default, if you don't specify a bounding box, it processes the whole overlap between the reference and the secondary image. So you get the whole frame. Say earthquake prediction is outside of the scope of this course. We're definitely in earthquake phenomena, right? Like measuring what happened rather than trying to predict something. So I have 7 minutes. Bring your questions.
Somebody's asking about it for the ICE top stack processing. Yes, in Tops app and in Top Stack, you can process a whole scene, but the Top Stack processor is really designed to set up processing for a given bounding box. So you really have to use a bounding box in the Top Stack as processors, because it needs to set up the processing it. And in fact, it's with the way the top slices are moving around, you really don't want to try to use it. There's no standardized frame that you can process. So you really need to think about the area that you want to process rather than a specific slice of tops data, because if you look through the different dates, that slice might be different on different dates. And by using the top stack processor setup, it'll automatically grab the relative slices for each date if you've downloaded them. You have to download all the data into one big directory full of SLCs, and you need to make sure that you've downloaded the slices that cover your area completely. So that's I use Sara federated query download to get a specific area. That's a very efficient way to do that.
So it takes a very long time as well to do the registration for all the images. So the more bursts that you're trying to include, the longer it's going to take. It might not be efficient.
To come please to the lobby, take the elevator to the second floor. When you arrive on the second floor, next to the elevator, there is a door that says floor, not the main floor.
Now about stitching.
It's like that, so you're gonna find
Stack
out
processing.
213. I'm gonna open
Right.
it. Thank you.
Maybe. Well, so this question, if my area of interest is larger than a SAR scene, can I use a bounding box to stitch 2 or more scenes together? Because frames in Sentinel-1 are basically just collections of bursts. I think you can choose a different set of bursts if they cross the frame boundary. That's okay. You do have to stitch them together in the setup of the stack. You got some noise.
Yes, so you define your bounding box, and if you've downloaded all the slices you need to cover that area, it'll figure out which slices it needs for each date to process the area, and it automatic with the Sentinel-1 tops mode, it can easily stitch multiple frames together because it's really processed by the burst. The slices are just arbitrary collections of bursts. With other satellites in strip map stack, if you're starting from SLCs, strip map stack will not be able to do any stitching of multiple frames. If you're starting from raw data, then strip map stack can stitch the raw data, but it cannot stitch SLCs. Shunran Liang did add a lot of extra code to do the stitching of the ALOS 2 SLCs in the ALOS stack processor. So that's another option for ALOS stack processing.
In some areas, there is only descending data available for Sentinel-1. Doesn't ASF release ascending data for those regions, or satellites are being operated like that only. So the ASF archive is a complete mirror of what is produced by the Copernicus project in Europe, run by the European Space Agency. What you see at ASF is what there is. If the data are missing, it's because they didn't acquire it. There are very, very few cases where something didn't copy across the first time. And sometimes you can check the Copernicus archive to make sure that it wasn't acquired. But generally speaking, if it's not there, it's because they didn't acquire it. And the reason for they didn't acquire it is often that they have a targeted areas that they acquire on every pass. These are usually tectonically active areas, other areas of interest, volcanoes, everywhere in Europe is acquired on every pass. But in areas where there is less interest, or that in their mission planning they identified as less important, they may not acquire every pass over those areas. So that could be why it's missing from the archive. It's just that there's a limited amount of duty cycle, the amount of power they have to acquire data. They can't acquire data everywhere, and so they have some specific targets that they acquire more data over. And if you're outside of those target areas, there may be less diversity in terms of viewing geometry for those areas.
Yeah, and obviously it's a European satellite, so they have excellent coverage over Europe, not surprisingly.
Yep.
They have over Europe, they have ascending, descending every possible pass. Over North America, they try to do ascending and descending over the kind of the west coast where there's the active San Andreas fault and other faults, but the whole eastern half of the United States, they do only ascending tracks in general. And that's been true since the beginning of Sentinel. And then in addition, there was for several years from when they got Sentinel-1B launched in 2016 until it stopped working in December of 2021. They were using Sentinel-1A and Sentinel-1B to cover different areas with different track angles. But then when Sentinel-1B went offline and stopped working, then some areas were no longer covered because that was the area that they had assigned to Sentinel-1B. I think they're starting to try to adjust the coverage a little bit, but because as Gareth was explaining, the Sentinel-1A satellite has a limited capacity and it was already at its capacity. So if they want to add coverage in some place, they have to remove it in some other place.
All right. Is there any direct way to find out which burst contains the earthquake, or is it trial and error? It's basically trial and error. You can draw an area of interest box around the earthquake epicenter. You can look up the earthquake in, say, the USGS earthquake catalog, or another earthquake, or a local earthquake catalog, and get some idea of where it is. I've worked on this a little. There are still errors in location from global seismology that can be more than 20 kilometers. So I would make my box at least that big around the epicenter that's provided. Most of the time, when I do this, I look at the earthquake catalog and the map of where the earthquake epicenter is, and I also look at the SAR image search like side by side, and I try and eyeball it to pick where in the frame the earthquake should be. And I'm usually sort of right, but yeah, you can still make you can still miss it or get just the edge of the pattern, and then you have to kind of process it again and try again. There is definitely some trial and error involved. The
question about whether if you wanted to have data that was acquired in a different mode, you would have to ask Copernicus to change their satellite operations. If it's not acquired, it's not acquired. There's nothing you can do about that.
Yeah, they don't like.
So Shang Li had this question about interferometry sensitivity, and for repeat pass interferometry, it's always considered ping pong because the satellite antenna is the receiver and the transmitter and this are the same. The other option of I forget what the other one's called, is only a specific to cases like SRTM or the Tandem X, where you have two antennas operating in bistatic mode. So for almost every case, you want to use ping pong equations.
Right, Eric, I think it's time you start. I can try and answer the rest of the chat questions.
Okay, so I'm going to start on the discussion of SAR satellites. Oh, where's the share? It's not going to be good. Where's my share screen?
Should be a little green button at the bottom.
Yeah, well, I see it. I had to go back to it. So let me see which is the are you seeing the presenter mode or the other one?
The other one with your notes.
Okay, where is the switch button? Hold on a second. This is a Keynote. I haven't used this with how to get the here it is. Sorry. Okay, let's go back
There
to
we
the
go.
beginning.
Now we can see the presenter view.
So I'm going to be talking today about the different SAR spacecraft and how do I get back to the beginning? So these are the lists of the older SAR satellites and that we've been used for many years. The big one for a long time was the European ERS-1 and ERS-2. ERS-1 was launched in 1992. ERS-2 was launched in 1995 or late 1994. For most of those missions, they had a 35-day repeat, and ERS-1 and ERS-2 are in exactly the same orbit. And they were set up so that they had ERS-1 and ERS-2 passing over the same place 1 day apart. So there's a lot of pairs of ERS-1 and ERS-2 SAR pairs that are just 1 day separation. And initially they were hoping to be able to use those 1 day separation InSAR pairs to make a global DEM. But as we discussed before, with there's all this atmospheric effects, and even though the coherence is relatively high with the 1 day separation in most places, there's still atmospheric changes over 1 day, and they found that there's just way too much atmosphere to make a good DEM globally. I actually did make some number of they call it ERS tandem interferograms and make DEMs out of them with the old ROIPAC software. We used that for the earthquake in Turkey in 1999. What's the name of that one? ISMIT. That was before SRTM was acquired. So nowadays, I mean, basically, once SRTM was created, people stopped using that repeat pass ERS tandem data to make DEMs. And the ERS-2 satellite basically worked until 2011. ERS-1 stopped working in 2001, I think it was. So there's a long time interval, almost 30 years of ERS data, almost 20 years of ERS data. So it's a really great archive of older data. ERS is all strip map data. There's no other modes. It doesn't have any complications, so it's easier to deal with in that way. RadarSat-1 was a satellite built in Canada by sponsored by the Canadian Space Agency, but it was actually launched on a NASA rocket. So it was a joint sort of a shared mission. So NASA had access to RadarSat-1 data for a number of areas, and a lot of that data is stored at ASF. But the way the arrangement was set up, the RadarSat-1 data acquired after they launched RadarSat-2, the follow-on in 2008, is no longer shared with NASA. So if you look at the archive of RadarSat-1 data, it's only going up to 2008, even though the satellite continued for another 5 years after that. The RadarSat-1 data is actually kind of very difficult to process. We had a whole system set up to process it with ROIPAC, but it's very difficult to process with ICE. I'm not sure if, I think Piyush had it working. I haven't tried it in ICE. I haven't processed any RadarSat-1 data for like more than 10 years, so I can't help you with that. Then the next satellite that was launched was the ENVISAT satellite. So the European Space Agency had built this ENVISAT satellite. ENVISAT was a very large satellite, the size of a large city bus, and it had both the radar and several optical instruments on it. And it was launched in late 2003, operated until September 2010. In September of 2010, they changed the orbit. They lowered the orbit to, so before that it had a 35-day repeat. Starting in September 2010, they lowered the orbit because they were running out of fuel. And it went into a 30-day repeat orbit. But that 30-day repeat orbit was also not being carefully maintained. So the baselines were continuously increasing because they were getting low on fuel. And then it failed completely in 2012. So basically the ENVISAT good data is between late 2003 and September 2010. And Gareth and I worked on the first earthquake that we know was well imaged by ENVISAT was the December 2003 earthquake in Bam, Iran that Gareth talked about yesterday a lot with the modeling. And then one of the last earthquakes was the El Mayor Cucapá earthquake in Baja California that I talked about a little bit yesterday, and I put the strip map app example on the server. ENVISAT also had a ScanSAR mode, but it wasn't really designed for interferometry. Whoops. The next satellite that's of very high usage is the Japanese satellite called ALOS. We've talked about that a lot. We use that for the strip map app demonstration. And the JAXA has sent all of the copies of all the data of ALOS to the ASF, and the ASF is putting them all online as a favor for JAXA to provide access to this data. That satellite was launched in 2006, early 2006, and it continued operating until April 2011 when they had some kind of problem on board, and it's just suddenly stopped working. Fortunately, it was very fortunate that they were able to get it collected data for the large earthquake in Japan in March 2011. So it kept working until just after that earthquake. I don't think there's any relationship on that. It's just a matter of luck. So then the next satellite that's fairly commonly used is the German space agency, DLR, launched a X-band satellite called TerraSAR X. So ALOS was a L-band, whereas the ERS, RadarSat, and MVSat are all C-band. TerraSAR X, as you can guess from the X in the name, is an X-band satellite, so it's 3 centimeter wavelength. It's significantly shorter than the C-band that we use from ERS, RadarSat, MVSat, and Copernicus 1, Sentinel 1. So it's a shorter radar wavelength, but it's a higher resolution. And they had a number of different modes that they acquired data. So they launched the TerraSAR X satellite in 2007. And then 3 years later, they launched a copy of it called Tandem X. And they fly the 2 satellites in orbits that are very close together so that they can operate the 2 satellites together for some of their data acquisitions and do the bistatic data acquisitions. And they use that to make this global DEM that was then edited and converted to the Copernicus DEM. TerraSAR X and Tandem X were both what the Europeans call a public-private partnership. That means that the DLR German government paid for a big part of the cost, but they also only have rights to give data for scientific purposes, and the company that made the satellites, which originally was called Astrium, but it was then bought by Airbus to become Airbus Defense and Space. So some places you can get data from the DLR through various announcements of opportunity. So they give away archive data pretty regularly. But some of the, if you want to get new acquisitions, it can be more difficult. And they also have this other arm of selling the data through the Airbus Defense and Space. The NASA is in the process of adding the TerraSAR X contract as a commercial small satellite data acquisition to give to researchers in the United States, but I don't think that is not going to be available to people outside the US. And it's only for people that are doing research sponsored by NASA or other government agencies. But those satellites are in this, as I said, they're in the same orbit. They are very close together, so they basically image the same place at the same time. Normally, they only operate one at a time, unless they're doing the special bistatic acquisitions, and that orbit repeat is 11 days. There was another one of these satellites built just a few years ago called PAUSE. It's basically another copy of TerraSAR X. It was built for the Spanish space agency, and that was launched in late 2019. And it's in the same orbit as TerraSAR X and Tandem X, so it can be used with for interferometry. And I believe they have it separated so that TerraSAR X has the 11-day repeat, but the pause satellite is in between, so that you have 4-day intervals and 7-day intervals between TerraSAR-X and pause. And there are some programs that the Spanish Space Agency is using to give data access to the pause satellite data. But again, it's in part a public-private partnership. So it's not just completely all online. And then the next one that was been used a lot extensively is the Italian Space Agency, ISCE, the Italian Space Agency in Italian. And it's a constellation of 4 satellites that they called Cosmos SkyMed. Again, this is a public-private partnership, very similar to TerraSAR-X. So the Italian Space Agency has had many programs to have announcements of opportunity to get access to Cosmos SkyMed data, especially the archive data. But a lot of the most recent data is more designed for commercial applications. It's another, they're all, the Cosmos SkyMed satellites are X-band, very much like TerraSAR-X, exactly the same wavelength as TerraSAR-X. It has the same kinds of modes, strip map, ScanSAR, Spotlight. And they had launched 4 satellites into the same orbit. Any one satellite has a 16-day repeat, but the separations between them were 1 day, 4 days, 7 days, 8 days. I know they're all separated in the orbit, so you could often get much shorter time intervals. I worked a lot with 1-day repeats of the Cosmos SkyMed data, which, because of its X-band, you lose coherence quickly, but with 1 day, the coherence is still high in most places. And if you're looking at phenomena that are rapidly moving, including a landslide that I was studying in Colorado, 1 day was enough to see significant motion. But there was also a lot of other intervals. So that's a valuable resource if you can get access to the data. There are some super sites that provide both TerraSAR-X and Cosmos SkyMed data for certain areas like Iceland, volcanoes, and Hawaii, and I think maybe some volcanoes in Central America. So that's an option for getting a little bit more public data. As I mentioned earlier, the Canadian Space Agency had a second RadarSat mission called RadarSat-2. RadarSat-2 was launched in December 2007, basically became operational in early 2008. Because of the nature of the arrangement with NASA, that then cut off access of NASA to the RadarSat-1 data. RadarSat-2 was intended to be basically fully commercial. There's been some programs to give out RadarSat-2 data by writing proposals to the Canadian Space Agency and getting small amounts of data for certain purposes. I've gotten a RadarSat-2 data for the 2015 earthquake in Nepal, the Gorkha earthquake, and it was quite useful for that. But in general, it's been very hard to get. And basically the data is somehow owned by the company that built it, MDA. RadarSat-2 is L-band, C-band, just like RadarSat-1. It has a 24-day repeat, but there's no compatibility between RadarSat-1 and RadarSat-2. You can't combine the two. There were some older satellites. The NASA actually launched the very first civilian radar satellite. We don't know what what the military did because they don't tell us, but NASA actually built a very relatively simple, and it was built very quickly as a sort of demonstrator and launched in 1978 as a satellite called CSAT. It worked very well for 110 days, but then they had some kind of problem on board and it stopped working. So there's only a small amount of data. This is a very old satellite, so it only was able to collect data and send it down to the ground immediately. So there's limited coverage, mostly over parts of the United States. But the very first differential interferograms were made with CSAT data back in 1988 or 89, before they launched ERS. So it's sort of the grandfather of SAR data. And the ASF has made a big effort to get all that old CSAT data. It was originally recorded on who knows what kind of tapes they used back in 1978, and ASF made a big effort to get all that data in digital form and put it online if you want to work with it. But ICE doesn't support that, so that's you're kind of on your own. There was another satellite the Japanese launched before ALOS. It was called JRS-1. It operated from 92 to 98. It was also L-band. That satellite, I used some of that data a few times, but it was not very much data and it had a lot of issues that made it difficult to work with. When I first came to JPL in 1994, it was to help with this shuttle imaging radar mission that flew in 1994 twice. I came actually between the first flight and the second flight. It was a radar system that was built at JPL in this huge frame that was then bolted into the shuttle payload bay. They opened the payload bay doors and they were able to operate the radar. It ran the shuttle flights for 10 days, collected a fair amount of data. And they were able to adjust the shuttle orbit so that the first flight in April of 1994 had the same orbit as the October flight on, I think, 2 days, or 1 or 2 days. And then in the second flight in October of 1994, they put it into the same orbit, repeating for 4 days in a row. So we have a number of interferometric pairs with 6-month repeats and 1 day repeats. And one of the big advantages of the SAR-C mission was that we had actually 3 different radar wavelengths on the same satellite acquiring data all simultaneously. The DLR and the Italian Space Agency built an X-band radar, so there's an X-band 3 centimeter wavelength. The JPL system was C-band and L-band, so we have these great examples of C-band and L-band data acquired with the exact same time intervals that we've used to look at how the C-band and L-band relate. Again, this is very old data that's not processable in ICE, but there are ways to process it with the old ROIPAC software. So then there's the newer spacecraft that you've been mostly talking about today. The older satellite, all the ones that I talked about before are no longer operating. The new one, of course, that we've talked about extensively is Sentinel-1. Sentinel-1 is owned by the organization called Copernicus that's supported by the European Union. It's a little bit different from the European Space Agency. They have different members, and even though the United Kingdom left the European Union, they're still part of the European Space Agency. So I mean, there's slightly different membership. The European Space Agency does all the design, launch, and operation of Sentinel-1, but the satellites are actually paid for and owned by this Copernicus organization. So to properly cite Sentinel-1, you should always call it Copernicus Sentinel-1, operated by ESA if you want. It's kind of a little bit complicated, but so they launched Sentinel-1A in April of 2014. They didn't get it into its final orbit until October of 2014, so you won't find any Sentinel-1 TOPS mode data until October 2014. They did acquire a little bit of strip map data with Sentinel-1 before they got it in the final orbit, including an important data set for us that covered the Napa earthquake that Gareth and I and a number of other people studied. They just happened to do a test swath over San Francisco before the earthquake, and then immediately after the earthquake, they happened to go over again and get this strip map image pair that covered the Napa earthquake, because the Napa earthquake was close enough to San Francisco. But in general, they only use this, now they only use the strip map mode for very few places like ocean islands where the wide swath of TOPS mode is not useful. So in general, almost everywhere it's TOPS mode since October 2014. They launched Sentinel-1B in April of 2016. It stopped, Sentinel-1B stopped operating in December 2021. They officially declared it lost a few weeks ago, and they've already built Sentinel-1C, and they're doing the final checkouts and getting it ready for launch early next year. So Sentinel-1A and Sentinel-1B and Sentinel-1C all have the same orbit. A single satellite repeats every 12 days. They set the phase between the satellites so that A and B were 6 days apart to get a 6-day time interval. Obviously, with only one satellite that we have now, we're back to a minimum of 12 days. When they get Sentinel-1C working again, it'll be back to 6 days, we hope. And it's C-band. The Japanese also launched another SAR satellite in 2014, almost the same time as Copernicus Sentinel-1A, called ALOS-2. The ALOS-2 satellite has a 14-day repeat. The previous ALOS satellite had a 46-day repeat. So ALOS-2, the satellite tracks are much further apart. With a short repeat cycle, the tracks are further apart. So to cover the whole area between the tracks, a lot of the data acquired by ALOS-2 is ScanSAR mode. If you want to process ScanSAR data, ALOS-2 ScanSAR data, you have to use the ALOS-2 app. It's a special app that is just for the ALOS-2 ScanSAR mode. Although ALOS-2 app also works for StripMap. There is, in some places, they also acquire ALOS-2 StripMap data, and with the ALOS-2 StripMap data, you can process it either with the ALOS-2 app or the StripMap app. There was an Indian satellite called RISAT-1 that was launched in April 2012. I'm not sure if that's still operating. The ICE software does have a reader for this. I think it was working a few years ago, but I've never actually used it, so I'm not sure if it's still working. That's a C-band satellite that had a 25-day repeat. And of course, our favorite mission that we're working hard to get launched is ISCE, that's now scheduled for launch in January of 2024, just a little over a year from now. And that has a 12-day repeat. It's not exactly the same orbit as Copernicus Sentinel-1, but it's going to be a similar 12-day repeat. And as we mentioned several times, NASA is building the 24-centimeter L-band radar for ISAR, and ISRO is building the 12-centimeter radar. radar. It's a band called S-band. There have been some military S-band satellites, but as far as I know, this is the first civilian S-band satellite that'll be operated in space. So I already mentioned a lot of this. The processing for these satellites is possible in ICE2. The strip map data from Sentinel-1 we work with the SLCs. Obviously, TOPSMA, we also work with the SLCs, as you saw in TOPSAP. ALOS-2 actually has 3 different modes: strip map, ScanSAR, and Spotlight. Spotlight is a way to get very high resolution in a small area. It sort of scans the radar as it goes past to keep the focus on a specific point, to get very high resolution in a very small area. You can process Spotlight mode SLC data with the ALOS-2 app, and the ScanSAR data with the ALOS-2 app, and the strip map data with either strip map app or ALOS-2 app. This RISAT, as I mentioned, we can process the SLC data from that. Then there's some other new spacecraft. The Argentine Space Agency launched 2 satellites called SAOCOM-1A and 1B. These were in 2018 and 2020. They have a 16-day repeat cycle. It's actually a very similar orbit to the Cosmos SkyMed orbits. They're intended to be sort of working together, but they have not been releasing the data very much. I haven't actually seen any SAOCOM data. So there is a reader for that in ICE, and it's an L-band satellite. The Japanese are getting very close to launching what they call ALOS-4. It's another SAR satellite that's going to be even more powerful than ALOS-2. They're still saying they're going to launch that by March of 2023. We'll see if that launch date holds. And it's going to have the same orbit as ALOS-2, 14-day repeat with the L-band wavelength. It's going to have even more modes, wider swaths. The Italian Space Agency has already started launching their Cosmos SkyMed 2nd generation satellites. These are in the same orbit as I don't know why that says any. It's the same 16-day repeat cycle as the original Cosmos SkyMed, and it's X-band. Again, this is data that's from a public-private partnership, so it's not generally available unless you get some of the limited data from the Italian Space Agency. There's another, the Canadian Space Agency has launched 3 satellites in 2019 all together. These are like smaller SAR satellites than the RadarSat-1 and RadarSat-2. That's called a RadarSat Constellation mission. They launched the 3 satellites together. Each satellite has a 12-day repeat, but the separation between them is 4 days. Because they're smaller satellites, they only acquire a limited amount of data, mostly over Canada, and the data is mostly available to Canadians, so it's not very useful for most people. And it's a C-band. There were some other satellites, as I mentioned earlier. There was this Spanish PAZ satellite, which is a clone of TerraSAR-X. It's in the same orbit as TerraSAR-X, gives some additional options of time intervals and data availability. And for as far as ICE processing is concerned, the PAZ data is processed the same way as the TerraSAR-X data, strip map data. There were some other satellites. The South Koreans had a satellite called COMSAT-5 that operated for some years. I think there is a reader for that in ICE. I haven't used it. I don't know and they haven't made that data very much available. You may have been hearing about the new commercial small satellites. There's Capella here in the United States. They've launched at least 9 satellites. They're all X-band. As far as I know, none of those satellites are in repeat pass orbit, so it's not possible to do interferometry. The European company, Finnish company called ISCE has launched now 16 X-band satellites, and some of those satellites are in repeat pass orbits and have a 1-day separation. But again, this is a commercial company, and they're not giving away much data. So that's basically the bottom line for overview of different satellites that are available. And I'm going to take a break now before we go to the next thing. Let's see, what time is it? 11. Let's come back at 11:20.
11:20 sounds good. Can you put up a message or something? That'd be great.
Stop that.
Okay.
Start this.
It's time. It's time to move on, I think, and start to look at atmospheric errors and how you might deal with them. I assume Eric is just preparing things behind the scenes. Maybe. I saw you move your mouse cursor a minute ago, Eric. I assume you're there.
Sorry, I scrambled to get things done during my break here. Where's the so the next we're going to talk about how to do atmospheric corrections. The key one we want to going to do in some detail is ionospheric corrections. We have a notebook to show the ionospheric corrections. Where's the screen share? It's not showing me the right one. Too many windows open. Outlook. Need a search tool here, or I need to close all my windows. Maybe I just share the desktop. Okay, so there's a notebook here under UNAVCO 2022 Troposphere and Ionosphere, Ionosphere, and strip map app Ionosphere. So we talked about this several times before. The ionospheric phase affects radar propagation through the ionosphere, which is an upper layer of the side of the atmosphere, between roughly I think 100 kilometers and 300 kilometers. It might go slightly, roughly. And all of the satellites signals go through the ionosphere, and one of the key things about the ionosphere is that it's what they call dispersive. That means that the radar propagation delay depends on the radar wavelength. It actually depends whether on the square of the wavelength. So it's actually, it changes very rapidly with wavelength, and we can actually use that dispersive characteristic to be able to separate what part of the radar InSAR signal is due to the ionosphere and what part is due to the ground deformation. The tropospheric delays are not dispersive. They're the same for all wavelengths, so we cannot use this trick of separating the wavelengths to estimate what the tropospheric delays are. But the ionospheric delays are actually can be very large at L band, and we really have to do something about to correct for this, because it's a huge effect. So maybe I need to make this bigger.
You might want to go full screen as well. That's better.
Does that look good?
Yeah.
Great. So as we talked many times about the different parts of the interferometric phase signal. There's the displacement of the ground. There's this effects of the geometry, the baseline, and the topography, and we also have these phase effects due to the troposphere and the ionosphere. So a lot of times people will talk about atmospheric corrections in general, but especially for radar, we really need to separate the troposphere, which is the lower 15 kilometers of the atmosphere, from the ionosphere, which is above about 100 kilometers, because they have very different the very different the ionosphere is dispersive and the troposphere is due to water vapor, and it's not dispersive. And then of course there's some additional noise. In the ionosphere, because it's full of ions, which are just atoms that have been split where the electrons are separated from the nucleus, and so there's all these extra electrons floating around in the ionosphere. The density of the is relatively low. There's you wouldn't see very many particles, but these large number of electrons floating around affect how the radar waves propagate through that part of the Earth's atmosphere. So okay, actually, so Haresh wrote these notes. I'm just reading them. So he actually writes a better definition of the ionosphere from 60 kilometers to up to 1,000 kilometers, but the main part is around 300 kilometers. And you'll notice that, in fact, the International Space Station is flying just a little, about 400 kilometers or 450. So they're still in the part of the atmosphere that has some ions in it, but they're above the main ionosphere. So they would not want to fly the space station at 300 kilometers. It would be constantly in this high electron density. The ionosphere causes because it affects the radar propagation strongly. It actually bends the radar signals as it goes through that section, and it causes these long track shifts, azimuth offsets. that affect the interferograms and can cause defocusing or difficulty with focusing. And then in the range direction, there's some amount of shift, but most of it is actually in the phase. It affects the radar phase. So it has a large number of effects. The tropospheric water vapor only affects the range delay. It doesn't have these other things. There's also something called Faraday rotation, where if the polarization is HH, it actually can be rotated as it goes through the ionosphere and come out as it could be all go through the ionosphere. If it's a very intense ionosphere, it could be start as HH and end up as VV, or start as VV, and it can rotate significantly. And that's another effect if you're trying to deal with polarimetry in areas of strong ionosphere. And the ionosphere also varies rather strongly with time of day and space. So there's basically two big areas of ionosphere. There's the high latitude ionospheric effects that show up as the aurora borealis and aurora septentrionalis. At the very high latitudes, when you see the aurora there, those are free electrons hitting other atoms and generating light. But there's also a big ionospheric effect during the daytime, where the sun is shining on the ionosphere, especially at low latitudes near the equator or near the magnetic equator, and it causes the electrons to separate during the day, and those electrons then start to reconnect to atoms after it gets dark. So in fact, the ionosphere is worse in the late afternoon and early evening. So in fact, these plots are showing the ionosphere at certain times. In the early morning, the ionosphere is relatively mild. And then the peak ionosphere is actually around 10 p.m. And this was actually a problem for the ALOS satellite, because the ALOS satellite was in an 10 a.m., 10 p.m. orbit, and they were mostly acquiring the SAR data at night at 10 p.m. And that actually was the time when the ionosphere was the worst. So ionospheric effects in the ALOS data are actually quite strong, very strong, and as for SAR data acquisition, that was well, they wanted 10 a.m. for the optical satellites to have the best illumination during the ascending tracks, but I mean the descending. But it was bad for the ionosphere. JAXA changed the ALOS 2 satellite orbit to have a 12 noon, 12 midnight orbit. So the ALOS 2 satellite has less ionosphere. It's not at 10 p.m. It's at midnight, but it still has much worse ionosphere on the ascending tracks than it has on the descending tracks. Or I might have that backwards. The Sentinel-1 satellites are in a 6 a.m., 6 p.m. orbit. And at 6 a.m., the ionosphere is pretty close to the minimum. So descending tracks of Sentinel-1 have very little ionospheric effects, and ascending tracks are the ones that tend to have more ionosphere, especially when you're close to the equator. And this is actually it's actually not controlled by the geographic equator of the Earth, but the magnetic equator, which is at a significant angle from the Earth. So you can see that the magnetic equator here is close to the geographic equator in South America. But if you go to Asia, the magnetic equator is up around 20 degrees latitude. So India, China, that area actually has strong, very strong ionospheric effects because it's at the close to the magnetic equator, even though it's not close to the geographic equator. So the key thing is that there's we want to try to separate this dispersive component of the phase that's different with the radar wavelengths. And one of the ways that that people have that the GPS satellites actually all the GPS signals are very similar to the same wavelength as L-band radar. So they have the same ionospheric effects. All the GPS signals and GNSS, Baidu, GLONASS, all those, the Galileo, they all go through the ionosphere and have ionospheric delays. And those satellites all use two different radar bands to be able to detect what part of the signal is due to the ionosphere and what part is due to the other effects like the position. So GPS data that you use is normally the ionospheric effects have been automatically removed by looking at the two different GPS signals, Galileo signals, and calculating what the ionospheric effect is and removing it. So we're going to basically do the same thing for the radar data. These TEC maps, that's total electron content, are generated from GPS data by the International Geodetic Service, IGS, and they actually use those ionospheric estimates that are measured by GPS stations around the world and then interpolate to give this global maps. So basically, what we do, since we don't have, for regular satellites, we don't have two different radar bands to use. We have to take the full band and cut it into two pieces. So basically, we have this full range bandwidth here, and we cut it into two pieces, a low band and a high band. With the NISAR satellite, we're actually going to have a separate high band acquired at the same time. So this whole separation step won't be necessary, but the calculations we're going to do with these two bands will be the same for NISAR as they are for other satellites. And by taking the two high band pairs, we can form we cut the range spectrum into two bands, and we actually form separate radar images for the first date and separate radar images for the second date, and then form a high band interferogram and a low band interferogram. Those basically have both the surface deformation effects and the ionospheric effects, but by taking the sum and the differences as shown in these lower equations, we can separate the dispersive ionospheric part of the phase difference between the high band interferogram and the low band interferogram, and the non-dispersive or phase change that's due to ground deformation plus troposphere. So these are the equations. And so basically, then this next part is explaining how, because it depends on the square of the radar wavelength, if we consider take the C band as the baseline, the ionospheric effects at S band, the 12 centimeter wavelength, are 3.9 times larger. Oh no, this plot is L band versus these other bands. So L band has 3 times larger, almost 4 times larger effects than S band, because it's the square of the wavelength. It's 18 times larger than C-band, and it's 57 times larger than X-band. So basically, if you're processing X-band data, you can ignore the ionosphere. At C-band, it's almost 20, it's 18 times smaller, but in cases of very strong ionosphere, you can still see the effects. And because of this along track shift, we can actually notice that there is a Ionospheric Correction module built into TopSap. We're not going to cover that, but it works basically the same way. So this is an example that Haresh published in a paper a few years ago. Let's make this smaller. There was a large earthquake in 2010 in Chile, southern Chile, called the Maule earthquake, a magnitude 8.8. This is an ALOS interferogram for the earthquake. And Haresh mentioned this yesterday, that by using this split spectrum technique, he was able to estimate what the ionospheric effect was. That's this calculation in the middle panel here. And by subtracting this from the interferogram, we get the corrected interferogram, which is much more close to the actual ground deformation. And you can see how much, these are L-band fringes, so each one of these fringes is 12 centimeters. The ionospheric phase effects can be up to several meters. So even though this is a magnitude 8.8 earthquake, we're only barely able to see the earthquake signal through the ionosphere. So that's an example of how important it is to do this ionospheric corrections. So going down here, I've already run this. What we're going to do is use the Hawaii ALOS data that we processed previously and add the ionospheric correction step. So I already ran this before. We're going to work in the same directory as we did before. That's the ALOS work Hawaii ALOS 1. You have to go in here and edit the strip map.xml file. In the previous strip map app notebook, it automatically generated this input file, and it put this do spectrum as false, but we're going to turn it as true because we want to do the split spectrum processing and we want to do the dispersive phase estimation. So we set both of those to true. We save it. And now we go back to strip maps ionosphere. It's just explaining how you need to set up the XML file. The notebook doesn't actually do that for you. So I ran this earlier. I in order to keep the original strip map app.xml file. This is a trick that you can use. You don't have to use an XML file that's called stripmap.app.xml. It can be called stripmap-iono.xml because I wanted to keep the original one before I edited it to do this editing step with you. I ran this previously using an XML file here called stripmap-app-iono. It's the same XML file, but with a different name. And you can specify the name of the XML file you want to use for your processing right here. And because we ran this whole processing with steps before, that allows us to redo the processing starting in the middle of the processing and only do the split spectrum processing. So the first thing it does is take the raw data. We actually have to do this modification on the raw data. And that's why the strip map app only does the ionospheric corrections for raw data. My Shunren Liang, who worked with me, found a way to do this split spectrum processing with the ALOS2 data that's only from SLCs. There's some extra work you have to do the filtering and with SLC data, but with the ALOS raw data, it's much easier. We can take the raw data and separate it into two SLCs. So actually, maybe it does work with the SLC. It's pretty simple. It's kind of a we just you do it in the Fourier domain. You can easily separate the two bands and write out. So we now have two new SLCs. If you look at the split spectrum directory, there's a high band and a low band. That's the high frequency and the low frequency. And each one of those has its own set of SLCs. And just like the regular interferograms, we have to do the resampling step to get the secondary SLCs lined up with the reference scene SLCs, and we have to do that for both the low band and the high band. So this running, it's just for the, and then after that we do the interferogram processing. This just takes a little bit of time. So are there any questions so far? Or I haven't been following the chat. One of the things is that we're working here with ALOS, the ALOS data that was collected in the fine beam dual polarization mode. So the total bandwidth of that mode is about 14 megahertz, and we're going to cut out two pieces, and those two pieces are less than 7 megahertz each. So, and they're only about 7 megahertz apart. So the difference between these frequencies is relatively small, and that means that the ionospheric estimates are going to be very low in accuracy. It's one of the things that we designed into the ISCE system, is having this extra high band that's going to be acquired completely separately. So even though we're collecting only 20 megahertz of data for most of the world, 20 megahertz band for the low band, we have this other band that's going to be, it's going to be narrower. It's only going to be 5 megahertz, but it's going to be separated by 80 megahertz all the way up at the other end of the overall band that ISCE has. So that very wide separation is going to give us a much more accurate estimation of the ionosphere than what is available from
I have a request to bump up your Zoom again. Zoom back in, because it's hard to read.
Oh, right. Sorry. Right. So we just did the interferogram. It's doing the interferograms. It has to do two separate interferograms: a high band interferogram and a low band interferogram. Yes, the ALOS2 app works for processing the split spectrum from SLCs for ALOS2 data. That's very important because the ALOS2 data is L-band, and it especially one of the other things about the ionospheric effects is that they tend to get larger with distance, even faster than the tropospheric effects. So if you're looking at a small area like this ALOS scene that we're looking at here is only 70 kilometers wide, it can look like it's only a simple linear ramp. But when you get over the ALOS 2 ScanSAR data is 350 kilometers wide, and you make an ALOS 2 interferogram, and there can be much more complicated ionospheric effects over the 350 kilometer wavelength. And it's almost finished here. Okay, so now we have the two interferograms, and each one of these interferograms is very similar to the interferograms that we process with StripMap app to begin with. But there's two full separate interferograms here. I'm going to skip this filtering step. Well, I should say something about the filtering. So Haresh added a very special type of filtering to the ionosphere because, as I mentioned, the ionospheric band, these high bands and low band for ALOS, especially for the ALOS fine beam 14 megahertz mode, are not separated by a very large amount. So they need to have a lot of smoothing. We need to use a smoothing of like 40, 50 kilometer wide smoothing to effectively reduce the noise to the level that we can actually do something with. So it's a much stronger filter. There's a whole number of options you can use to try to get a better filter for the ionosphere. But I'm going to skip that step because I ran it before and just go to the display step. And this is where we actually see the two interferograms. On the left here is the full band interferogram. This is without any, with the whole range bandwidth. The center one is the low band interferogram, and the right one is the high band interferogram. And you can see those two interferograms are similar, but not exactly the same. And so what we're going to use is the difference between these two interferograms to try to estimate what the ionosphere is. So they don't look completely different. They look, but they are different enough that we can be able to separate the ionospheric signal from the deformation signal. You can see also that there's this deformation from the dike injection that's in both of these interferograms, and by subtracting the interferograms, we separate that ground deformation signal from the and this next plot is the plot of the difference. You can see there's some difference in the area of the deformation signal, but by looking at how the difference depends on the two bands, we can then the next step is to do the phase unwrapping. These plots here are the wrapped phase. You also do phase unwrapping. I'm going to skip that because I ran that earlier. You can run that step. And then finally, we get to this step here. It's the ionosphere calculation. So it's going to use, we have to do the phase unwrapping. So this split spectrum technique requires that the area be coherent enough to do phase unwrapping. If you have only a very small island in the middle of an ocean, then likely your ionosphere correction isn't going to work well because you can't, or if it's an area where the coherence is low for some reason, so over water, lakes, oceans, whatever, then it won't work well. But once we have those two unwrapped interferograms, then we can estimate what it estimates both the dispersive component that's due to the ionosphere and the non-dispersive component. No, it's Hawaii, it's Strip Map app, not the Tops app. We're doing the Strip Map app, Ionosphere Corrections. And it's also it has some sophisticated processing to deal with the places where there's ocean, not to include the ocean when you're doing the filtering. It takes a lot of extra work to get a good ionosphere correction estimate. So now we have these two basic, this is after running the ionosphere calculation. We have on the left here, the ionospheric phase, which is the dispersive component. And you can see now that big ramp of phase that we had in our original Hawaii ALOS interferogram, all of that is due to the ionosphere. The actual interferogram, that means we can correct for this and remove all that signal. And over here on the right is the non-dispersive component that is a heavily filtered version of the actual ground deformation. We don't need to use this because we're really only interested in the ionospheric correction part, but we plot it here just so you have an idea. You can see it's very heavily smoothed version of the interferogram. You wouldn't want to use that for analysis. So the next step is to actually apply the correction, and we get the original interferogram here on the left and the interferogram. So this is still the a wrapped interferogram after we've applied the ionosphere correction, but you can see that now that huge ramp of phase across this part of the island is almost completely removed. There's still a little bit of ramp here, and that's likely due to the troposphere water vapor, because the water vapor is not dispersive. We can't estimate that from the split spectrum technique. So finally, the last step is just to geocode the corrected interferogram, which takes a little time. And I already plotted this earlier. This is our final geocoded interferogram. On the left is the original uncorrected interferogram, and on the right is the final interferogram with the ionosphere correction. So if you're dealing with L-band data, you really want to do ionosphere correction. And we're gonna, for ISCE, we're going to be likely doing this correction. We're doing the correction calculation for you and providing that as a separate layer in the ISCE products, because some people might want to see what it looks like separately before the correction, but then in the software you could easily subtract the ionospheric effects and get a cleaner interferogram. There's a whole bunch more information here about how to do more different types of filtering. In some cases, the ionosphere has a very strong lineation to it. We won't have to go into too much detail of why that happens, but especially at low latitudes, there's can be a strong lineation to the ionosphere, in which case you want to do a filter that has a non-uniform shape.
You have a request to show the full figure. If you turn off if you right click in the area where you have the plots, you can turn off the scrolling and actually show the full thing.
Oh,
yeah, that.
Right. Yeah, so I forgot about that. Yeah, so here's the full plot. There is a big elevation change across this scene as you start to go up on the edge of Mauna Loa, and so some of this remaining map is due to tropospheric water vapor. Hawaii, as you might expect, has a significant amount of water in the atmosphere, so we can expect there's significant water vapor effects in addition here, but the ionospheric effects are much larger in general than the tropospheric effects. So at L band, so the fact that we can correct for this ionospheric effect is a big start to getting a more usable interferogram from L band data. So this is the Gaussian kernels here are just a ways of how the filter is applied. We convolve this kernel with the interferogram. You have to look up convolution to understand what but it's a Gaussian shape that we convolve with the interferogram to do the filtering. And by using a different shape to the Gaussian kernel, then the filtering will be stronger in one direction and less strong in the other direction. No, these cells take time to run. Oh yeah, there were some mistakes in some of these cells that I forgot to update. If it says if you get an error importing GDOL, then you have to change the line to say from OSGeo import GDOL. They changed something in the way GDOL is installed on the system from last year to this year. So I thought I had updated all the, but several of these plotting steps they import GDOL again, and that was a bad idea. I don't know why it's set up that way. Here, yeah, I had to change this here to from OSGeo import GDOL. We'll fix that and get a newer version of the notebook later today. But I thought I had fixed all of them, but I think this last one is not fixed. It's kind of a pain, but stuff changes with software. That's why we have to keep maintaining it. It's not you could buy a car and the car keeps running for 30 years. I mean, you have to fix, sometimes you have to fix the brakes or the shock absorbers or do some overhaul on the engine, but basically it kind of keeps working the same way, but software kind of changes without you doing anything, so it has to keep being maintained. So I think this is basically the final result of the Ionosphere correction. This is before this is in the radar coordinates, and this is the geocoded version. So this is our final result. TOPS Ionosphere correction works basically the same way. Has a little bit slightly different interface. The Ionospheric correction that's in TOPSAP was written by Shunran Liang. Haresh implemented his correction in StripMap app a little bit differently, but they're doing the exact same calculation. They're just implemented by different people and almost the same way, but slightly differently. Some of the parameters are different, but basically it works the same way, except that for TOPSAP, because of this along track shift component of the ionospheric effects, the TOPSAP Ionosphere correction actually calculates what the along track shift is and applies that. And so the other thing to remember if you're going to use the Ionosphere correction in TOPSAP is to turn off the ESD in general, because almost all of your shifts that are in the TOPSAP are due to the ionosphere. So you can either do the empirical estimate with ESD that's a constant over the whole scene, or the estimate with the split spectrum method of ionosphere correction. Sometimes the ionosphere correction won't work. Again, it has to do the interferograms for the two dates. And if your interferogram has large areas of forest or other low coherence areas, then the ionosphere correction won't work well. It really depends on what you need to do. Okay, so I think I'm going to switch now to the
Exatamente, não vejo, eu vejo assim uma coisa.
where's so for the tropospheric corrections, there's a
There are a load of questions now about how the ionosphere phase is correct. It's calculated. I think, well, there's an equation earlier in the notebook that explains that. Once you've identified what the dispersive phase is, you can go in and get that. How do you the central low frequency and high frequencies determined? They're based on the bandwidth of the signal and the frequency of the radar. And you split the band in half, or you can even slice it thinner than that if you want to. I mean, by reducing the bandwidth, you reduce the resolution of your interferogram. So there is a trade-off, but that's basically how you do it. And there's a lot of details there that I think are kind of touched on earlier in the notebook. Go back and read that, I would say.
Now PowerPoint's not behaving well with the chat window, so I'm not going to be able to read the chat while I'm doing this PowerPoint slides. So the tropospheric delay, this is a set of slides that Haresh prepared last year, and I made some small modifications for. Haresh was busy to this. Again, we're doing InSAR and trying to. Most people want to look at the ground deformation, like this BAM earthquake interferogram here. That I'm sure Gareth recognizes. We want to see this, almost everybody wants to see this ground deformation, but there's this, so that's this is the notation that Haresh uses. The atmospheric delta phase, DIS is the displacement, delta phase, ATM is the atmospheric phase, and by that, atmosphere in this case could be both the ionosphere and troposphere, but this particular lecture is about the tropospheric effects. Then there's the geometric parts and the noise or decorrelation. So for the tropospheric delay, this also applies to the ionosphere. Basically, the atmosphere can be very different on one day than it is the next day. You've all seen that the weather one day is different from the day before. That happens all the time. So the radar waves on the first acquisition go through maybe a thin cloud with no water in it, and the second day they go through a cloud that has a lot more water in it, and that causes a change in the index of refraction, which also causes a phase delay. And basically, we could try to estimate all these components together. There's actually a small effect of the water droplets in the clouds. We don't have a good way to estimate that in general, so we usually ignore that. But then there's these other terms here that we call troposphere in this equation, which are the dry delay, which depends only on the atmospheric pressure here. one of the effects of on the of the troposphere on the INSAR is just due to the dry atmosphere. Basically, the overall weight of the atmosphere, which you easily measure with a pressure gauge. This is just the standard atmospheric pressure that weather people always talk about, and atmospheric pressure generally tends to vary with both days, weather, and with season. So and it varies with height. So we actually get a significant INSAR phase component that's proportional to height. That depends on the air pressure change between the first date and the second date. And then these second two terms depend on E, which is the water vapor in the atmosphere. There's actually two different parts. One depends on the E over the temperature, and the other depends on the E over the temperature squared. So if you have a measurement of water vapor pressure, you need to use this equation to actually estimate what the range delay is. This cloud effect, we haven't really been trying to do any corrections for, because we don't have good ways of measuring the water vapor in clouds. This is not water vapor. This is water droplets. There's a separate effect between water vapor, which is the evaporated part of the water, and the actual droplets that are in the clouds. So normally the cloud droplet effect is really small, and we ignore it. And then, of course, this last term here is the ionosphere, what we just talked about. So there's basically two different ways of estimating the tropospheric delay. One is to look at how the phase, interferometric phase is, we estimate it from the data, or we get some independent data from other satellites, from GPS data, or from weather models. So the empirical approaches are basically one of very effective motion is the time series analysis. So if we have a large number of interferograms and we do the time series analysis, if we're looking for something that's moving gradually with time, and the atmosphere is sort of moving back and forth, by looking at the long time series, we estimate we can estimate what the velocity is by averaging out the atmosphere over time. And that's a very effective technique, and that's very, very commonly used. There's other methods. MintPy includes this also, which is, as I mentioned, there's this effect of the both the dry atmosphere and the water vapor varies with elevation. So if you have an area that has a large amount of elevation change, like many kilometers, then you'll often see interferometric phase that's proportional to elevation. And we can actually estimate what that proportionality constant is, and try to make an empirical correction. If you're trying to look for a signal that's also relatively correlated with topography, that'll remove the signal too, and so that's an empirical approach that can work to some extent, depending on where you're trying to work. And then there's using data from other independent data sources. So in the past, the ENVISAT satellite had actually a very excellent imaging spectrometer on the board called MIRIS. So for ENVISAT data, they actually acquired this MIRIS data at exactly the same time as the radar data. So we can use this MIRIS data to correct the water vapor content in the atmosphere at the exact same time as the INSAR acquisition. There's also these satellite instruments called MODIS. There's MODIS sensors on both the Terra satellite and the Aqua satellite of NASA, and those We've used those in the past to estimate water vapor corrections for InSAR data. The issue is that the MODIS data it's not acquired at the same time. Usually it's within an hour or so, but MODIS is collected worldwide all the time. So that's an excellent water vapor data set. The old MODIS satellite sensors are getting old, and they're now being replaced by some new ones that I forget the name of. But there's NASA and satellites that can be used to measure water vapor. We can also, in GPS processing, the GPS people also look at the time series of GPS, and they estimate what part of the time series signal is due to the troposphere that's changing during the day, and what part is the ground position. So they estimate tropospheric effects also. They also look at how the effects are different with different satellites, because there's a lot of different GPS satellites. There's a whole, but that's only available where there's GPS stations. There's methods to use GPS stations plus atmospheric models, but the main tropospheric corrections that most people do, other than the time series analysis, is using weather models, global weather models or local weather models, to estimate what the water vapor is at a time that's pretty close to the time of your SAR data. And there's both the forecast models and the reanalysis, where they go back and reanalyze data to get what the weather was in the past. And so that's a very popular method. And this is an example of using a interferogram from the ENVISAT satellite, where we had the MIRAS data on the satellite. In this case, the interferogram on the left has a significant gradient across it. These are C-band fringes, so they're only 3 centimeters each. When we saw that big gradient on the ALOS satellite, those were L-band fringes, so it was a much bigger signal. The tropospheric signal is usually on the order of a few centimeters up to 12, maybe 15 centimeters in the worst cases. In this case, because we're using ENVISAT data, there's the MIRAS acquisition. MIRAS is using reflected sunlight, so it's only available for the descending tracks that were acquired during the day. But it was acquired at exactly the same time, and it measures the water vapor, so we can do a correction and get a corrected interferogram from ENVISAT that has the water vapor effects removed. There's another example here. This one also works quite well. It's very similar. And this is an example where we used on the left is the interferogram, in the middle is the interferogram corrected with the MIRAS water vapor measurement, and on the right there's a correction that's estimated from one of these weather models. This is a weather model called the ERA interim, which stands for ECMWF reanalysis interim, which ECMWF is the European Center for Medium Range Weather Forecasting. So this is an acronym of an acronym of an acronym, but that's one of the more popular and relatively accurate sources of weather model data. Although ERA interim is no longer available, they now switched to something they call ERA 5. It's version 5 of the ECMWF reanalysis. These slides were made some years ago. So with the weather model, we actually use the information that the weather model has about how the water vapor is varying with elevation. And we use the weather model estimate of the atmospheric pressure. The atmospheric pressure estimates are very good, so we can calculate what the atmospheric delay is due to the air pressure, dry air pressure change, And we can also estimate how much of the atmosphere, what's the gradient of water vapor with height, and how that gradient is different between the two dates, and use that information from the weather model combined with the DEM to estimate what the tropospheric delay is, with pretty good accuracy at large spatial scale. So the weather models, the ERA 5 is now available at 12-kilometer resolution. The old ERA interim had 70-kilometer resolution, so obviously it's not going to have much detail at 70-kilometer pixel size. But because we're with ERA 5, it has 12-kilometer spacing between the model outputs. But because it includes this elevation information about the water vapor, and we have the very high resolution DEM, we can estimate what the water vapor delay is at the resolution of the DEM with a fair amount of processing. And there's this is an example of from Roman Jolivet paper, Jolivet et al. 2014. On the left here is the original interferogram, and on the right here is the path delay that's due to the water vapor, the wet delay, and in the middle here is the change due to the dry part of the atmosphere, the pressure change. This is smaller in this case, although this is L-band, C-band NVSAT data. So it's incoherent in the mountains. You would see a little bit more dry delay at the higher elevations here. This is Los Angeles. These are the San Gabriel Mountains. But the prediction for the tropospheric correction here is a combination of this dry delay due to the dry part of the atmosphere and the wet delay. And so that's a calculation that's built into a program called PyAPS that you can use within MintPy. Yunjun's going to talk about that tomorrow. This is another example over Hawaii. This is the Kilauea is just here in the right here in this part of Hawaii. This is ALOS data. I don't know why the ALOS data is decorrelated. Maybe it's a long time interval. Usually the L-band data has better coherence even over the forest here, but it's you can see which parts from Hawaii are covered with forest and which parts are bare rock by the coherence. But there's also you can see what this interferogram has a very strong variation of interferometric phase with height, and because this is L-band, there's over 60. There's 60 millimeters or 6 centimeters of I mean they're of interferometric phase. In this case, the ERA interim, the ECMWF reanalysis old interim project gives a prediction that's pretty good. The MIRA is another instrument that was on a European satellite. It's similar to MODIS. That gives a little bit less accurate estimate. And in there's an even better estimate. The NARR is a local weather model that's calculated for parts of the United States. It's only available for, I think the NA here stands for North America. North America Rapid Refresh. So that's a local weather model that's only available for North America, but it has a better resolution. Globally, the ECMWF data is available globally. So areas outside the US, you want to use ECMWF, which is now ERA 5 and not ERA I. And Haresh did this in his thesis work some time ago, looking at how the tropospheric delay estimated from the weather models varies. The gray dots are the estimated tropospheric delay from the weather models, and the blue and red circles are the INSAR time series. I'm not sure why there's two different INSAR time series. You have to ask Haresh. But you can see that there's this very strong seasonal variation in the radar phase. And that seasonal variation between the winter and the summer, many places, there's a huge difference in the water vapor content and atmospheric pressure between the winter and the summer. So we're able to actually estimate a large part of that seasonal variation of the tropospheric delay. And that by estimating that and removing it, we can greatly improve the quality of the time series. And Yunjin will be talking about that tomorrow. This is just and this is a map actually showing the amplitude of that seasonal variation of the phase delay. And in fact, even though it's fairly strong here in Los Angeles, in general, the blue dots here show that Western US generally has less water vapor variation in the atmosphere than the eastern part of the US. And that's mostly due to all that warm water in the Gulf of Mexico. So if you're doing something in the eastern US, you need to do even better atmospheric corrections than we do here in the West. And this is just a comparison of the water vapor estimates from GPS data with the dots, MODIS data, the NASA satellite, the ECMWF reanalysis, and comparing each one of those, you can see that there's this high correlation between the tropospheric delay estimate and the topography, which is part of how we do a more accurate correction estimate. And this is just another plot from Haresh's paper that shows how you can improve the quality of the estimates by quite a bit after doing the corrections. And this is just a link to Haresh's paper from 2015 and Roman Jolivet's paper from 2014. The Pi-APS program that we use with MintPy is based on Roman Jolivet's paper, so that's going to be an important reference. There is a notebook in the directory here for doing tropospheric corrections with Geckos. We don't getting late here, so I'm not going to go through that. Just go through this overview of how the atmospheric corrections are done, and Yunjin's going to describe better how to do these corrections within MintPy. In general, it doesn't matter too much whether you apply the corrections to the interferograms directly before putting them in the time series analysis, or you remove the tropospheric phase as part of the MintPy time series analysis. These days, I think most people at least do the tropospheric corrections within MintPy or other time series analysis, as opposed to trying to apply it to the interferograms beforehand. The ionospheric corrections you have to do to the interferograms because there's no way to do that later. You have to get that from the SAR data, but especially with these weather model based tropospheric corrections, we can do that after we've already done all the InSAR processing and put it into the time series analysis. So Geckos is a tool that was developed by Zhenhong Li and Chen Yu at they were at the University of Newcastle at the time they developed it. Around a year ago, Zhenhong Li, who I worked with for many years, even when he was a student, you'll see a number of papers that I was a co-author on with Zhenhong Li. He's been working on atmospheric corrections for a long time. They did this Geckos correction. It uses the ECMWF weather model data and the DEMs, and I believe it uses some part of the GPS data that's available to do it does the full zenith delay estimation for you, and then they provide as a product. I actually had to stop using Geckos in the last year because Zhenhong Li moved from Newcastle, England to a job in China, and we're not allowed to use any servers in China. Our JPL computers actually will not receive any emails sent from China, .cn addresses. We can't go to there's a block on all our computers. We can't actually download anything from China. So in fact, I had to stop using Geckos about a year ago when they moved their whole Geckos servers to China. If you're not a JPL or some other institution that blocks access to China, you can still use Geckos. And that notebook that's in the repository explains how to use Geckos to do the corrections for interferograms. But especially after they changed the Geckos servers, I started using the ERA5 corrections within MintPy myself, and so I'm not going to try to explain the Geckos.
Geckos has this inverse distance weighting thing that it integrate GPS estimates of troposphere delay in with the weather models, and there's some kind of weighted sum of the two. But that's not the product which is freely available. You kind of have to ask them nicely to do that. Do you know anything? There's a question in the chat. Do you know anything about David's latest thing, Radar?
Radar, yes. So David Beckhardt and some of his colleagues have been working on generating this new tool called Radar, which is basically a big improvement on the Pi APS program that we've been using for 10 years. It also uses the ECMWF reanalysis products. It does but it actually has a way to do ray tracing of how the radar path is going through that gradient of the atmosphere, which can give a slightly improved estimate of the slant range delay. I mean, all these other calculations, they just assume that that we're only looking at the path delay for a vertical propagation, and then do a calculation of how to correct that vertical to a slant path delay, but it's not actually calculated along the diagonal. And Radar is trying to do that. There's I think they actually released something just a few weeks ago that may be a working version. It wasn't fully working last time I tried to use it, but it is supposed to be more accurate. And in fact, we are planning to use Radar to calculate the tropospheric delays for ISCE. So ISCE data products will have an estimate of the tropospheric delay as a separate layer it comes with your ISCE interferograms. It won't be applied to the interferogram. in advance, but it'll be a layer that you can apply later if you want. And that'll be calculated with radar.
Great.
So I think maybe we should go to the next break. What's the, we're running over here.
Yeah. This is important though. Yeah, maybe another 10 or 12-minute break. Maybe come back at 12:45 Pacific.
12:45. Okay. Let's see. How do I get to the other? Where's my mouse? Two screens and two programs running at the same time is confusing.
And I get the sense, Eric, you don't have a shortage of browser windows open.
All right. I have to. Why is it not showing my mouse? How do I get this out? Where's the mouse? For some reason, it's not showing me my mouse. Ah, okay. And yeah. 12:45.
Yes.
Why is it not showing my mouse? It's craziness. I don't know what's going on. Well, should say 12:45. I'll figure out how to change it. Let me stop share. And I want to change the slide. Oh, the Mac just decided it wasn't going to show me where my mouse is. Well, I'm not doing the next exercise, so we'll just we won't have the slide screen.
How about I have a little timer app. I can throw that up.
Sure. Seems I confused my Mac by moving the mouse too many times or something.
It's okay.
Okay. We're back. Is Forrest around? I see he's on. There you go.
Yeah, hi. How's my audio?
Sounds fantastic.
Great. All right, are we ready to get started?
I am. Thank you for everybody else.
Great, sounds good. All right, so I'll be pitch hitting for Franz Day as he couldn't quite make it, but today we're going to be, in this session, we're going to be talking about pixel offset tracking and how that can be useful to you, like kind of in addition to your InSAR workflows, but also just solely on its own. So the notebook we're going to look at is in the 4.3 folder of the UNAVCO directory, and then it's this IPython notebook called Autorift.ipynb. And Gareth, can you let me know when I'm at a good zoom level?
Sure. Maybe one more. That's pretty good.
Pretty good.
Anyone
Would that
online
be-
having problems reading it, this is the time to tell us.
All right, I'm going to assume that's good. One important thing for this notebook is it does use a different kernel than the one we've been used to using, just because Autorift has some strange dependencies, which is a program we'll be using. So if you click over here on this side of the notebook, it should already say Autorift, I believe, but if it doesn't, click on this and select the correct kernel. You know, most of our workflows have been using the UNAVCO kernel, but we're going to be switching to Autorift for this one. And then once you've selected that, you'll want to go through and just restart the notebook to make sure that the kernel is working correctly and everything.
So if we don't see it, is it a case we should shut down our servers and start them up again?
Yes, I believe so.
Okay. That's the case for me anyway. So
Oh, okay. So hopefully we can get that figured out. While that's going on, I'm just going to run some cells here right quick in the beginning to install a additional package. Just going to clear that output to get it out of there. And then we'll start looking at using Autorift once we these ones loaded up. Okay, so Autorift and other pixel offset tracking software are a way to track motion between images, similar to InSAR in terms of the type of data you get out, but very different in terms of the speed of motion that you can actually observe. So as opposed to C-band SAR like the Sentinel-1 satellites, which between images can observe about 2.5 or so centimeters of movement, pixel offset tracking or feature tracking can observe motion on the order of several meters to tens of meters at a time, and sometimes even up to a kilometer or more. And so this technique is really great when you know that you have features that are moving much, much faster than are detectable by InSAR. And so the original conceptualization of this method was based in manual feature tracking. The basic idea is you take an image of a place and then you come back sometime later, take another image. And let's say, for instance, you're looking at a landslide that is slowly moving downhill and you've got a tree that's on top of it. If you take a picture of that place on the Earth and identify where the tree is, and then come back later to a second image and see that because the landslide has moved downhill, it's kind of taken that tree with it as it's moved, you can find the location of the tree in both images and then calculate the distance that tree has moved. And using that type of method, you can figure out how fast that landslide has been moving. So that's kind of the manual feature tracking approach. But you know, if you want to do that over large areas, that becomes basically, it takes way too long very quickly. So people have developed these automated approaches. And these automated approaches rely on something that's called template matching, where basically you use an automated process to create a small chip of an image. So basically imagine you take a part of an image that is like 4 pixels by 4 pixels, and you move it around an area and compare it to a second image at a bunch of different points and see where that little chip, that 4 by 4 pixel chip you took out of the first image, where it's most similar to the second image. And this GIF that I'm showing here on my screen is kind of a representation of that. Imagine this is one-dimensional. This red square is the chip we're moving along the second image, and we're calculating the similarity between this red chip and the background image the whole way through.
Hi, Forrest.
Hi.
Could you pause and then maybe re-demo the environment again? I believe, including me, several others has problems to choose the kernel. I actually
Really?
still cannot, yeah,
You're not
find the
seeing
kernel.
it.
No, I'm not seeing it, and I'm trying to install it using the create Conda environment thing, or create OSL environment thing.
Yeah, and I have actually restart my server and then it still did not show up.
Shoot, this is unfortunate. It's always worked. You know, works on my machine.
Do you mind maybe just for demonstration shut down and log out and log in again so that we can follow you exactly?
Sure.
Thank you.
So there we go. I'm fully shutting down my server. Hopefully this won't take us too long. All right, we're back in and I'm seeing these. I'll switch back to the UNAFCO environment, just show this as possible. I believe it should be this one. There also might be this one. Do you happen to see this one, Eugene, at all?
Let me see. No, I actually see, no, I don't see any. I only see the autorift.ipymb at the very bottom. On the, yeah, I only see that. Among the top one, the start preferred kernels, among this category, I only have 3, and there's no Autorift.
Okay, we'll try. I'm just going to try loading the main dependencies and see if that environment will work. Shoot. Okay, well, I think I might have to go behind the scenes with Alex and make sure for the homework that this environment is available. And for the meantime, I might just have to go ahead and demo this notebook.
Yeah, I think that sounds
and have
good.
just people
Yeah.
go along. All right, I'll just go ahead and refresh this. Okay, so as I was saying, template matching or feature tracking is basically an automated way to identify a point in a second image that bears the most resemblance to a patch from the first image. So what this looks like, again, is imagine this red box is from your first image, and the blue box is where it happens to be in the first image. If you're calculating similarity using some statistical index, then this similarity will reach its peak when these two boxes overlap. And using this, you can actually find the place of highest similarity between these two in the second image and calculate an offset or a displacement between a first and a second image. And there are multiple ways of calculating the similarity in this context. Autorift, the main package that I'll be talking about today, uses the normalized cross correlation to compare the similarity, but other algorithms first transform the data into the frequency space and then form a similar cross-correlation analysis in that space. And that does have some benefits. Particularly, I think you tend to get a little more stable answers and you get fewer areas of no data, but the standard normalized cross-correlation tends to be a bit faster. So some of the benefits of the Autorift algorithm is that it takes NumPy arrays as inputs. So as long as you can get your imagery data into a standard NumPy array, you can process it with Autorift. So I've seen people even use it with kind of regular camera imagery, looking at the sides of features such as time-lapse cameras or something like that. But it's typically used in our context with either aerial imagery, optical satellite imagery, or synthetic aperture radar imagery. Under the hood, Autorift, which stands for Autonomous Repeat Image Feature Tracking, is using the OpenCV library to perform this template matching and the other imagery functions. So it's built on some pretty stable and well-performing Python packages that perform really well. Another really cool thing about Autorift is that there's a project currently spearheaded by Alex Handwerger at JPL called the It's Life project, which is using this Autorift technique with feature tracking to measure glacier velocities around the entire Earth. And if this is something that is really interesting to anybody in the audience, I'd suggest checking out their website. I believe that it is just its-live.jpl.nasa.gov. They have some really cool notebooks that show this data and show off what you can do with it. So when you're performing these types of feature tracking analyses, there are a couple of key parameters to keep in mind. The first is the template patch size, and that is just the size of the little patch that you're moving around in the second image to find where the closest match is to it. And this tends to vary somewhere between maybe 4 pixels to 32 pixels. And what tends to happen is as you get larger patch sizes, you can detect slower forms of movement, but you tend to lose a little bit of resolution as you do that. The second parameter that's very important is the step size. This is basically if you have a patch like this, and you're finding the match for that patch, how far over in the image do you move before creating your next patch? So this figure here is demoing basically the center of a given patch. And then if you move from red dot to red dot, that would be the step, the distance you're moving between the patches. And the important thing to remember here is that if your step size is larger than your patch size, then all of your offset measurements are going to be independent. Basically, no part of patch A is going to be in patch B next to it. But as soon as your step size gets smaller than your template patch size, then you're going to start to have some dependency between those things. That's not necessarily a huge issue, but it's just important to remember that those aren't necessarily always independent measurements, even though they might be represented by different pixels in the output image you get. And another key point is that step size ends up being the output resolution of your imagery. So let's say you're starting with imagery that has a 10-meter pixel size, but then you are using a step size of, let's say, 8. All of a sudden, that means your output measurement image showing where the pixel offsets are is going to be 80 meters instead of 10. So that's good to keep track of. The next important parameter is called your search distance. This is basically how big of an area are you going to let this patch search for a good similarity match. So this typically varies anywhere from 64 to 256 pixels, depending on how fast of movement you're expecting to see. You know, for very slow movement, you could ramp this all the way down to just a few pixels, but if you're using this technique to measure something moving much faster, like a glacier, you might want to ramp this all the way up to much larger, a much larger distance. The only caveat here is, you know, as you increase your search distance, you're also increasing the amount of time it's going to take you to perform this analysis, because, you know, you're covering more area with each patch. And then this last parameter, I'll talk about a little bit in a second, but it's oversampling. Basically, are you going to do some upsampling of the images to try and get a little bit more accurate a result? But I just wanted to show this figure, kind of walk through this figure real quick. This is a figure pulled right out of the main paper describing Autorift that was published, I believe, last year. And basically, this shows you how all the different parameters I just discussed are interacting. So you're starting off with an image patch at each location. That's kind of represented by the red dot. And then you're moving it around inside of the source image patch, which is bounded by basically the search distance. And this would be the search distance here for this patch. And you're going around and you're comparing this patch with every point in this search distance, and you're creating a normalized cross correlation surface. And this is what this would kind of look like. So here you have your X and your Y, and then on the Z axis here is your normalized cross correlation at all these different points. And here you can see that we're getting a spike or a peak. And this is our place of maximum correlation. And this would be the area that the algorithm would count as the place with the highest similarity, and therefore the place where the patch has moved from between the first image and the second image. And so by calculating the distance between where this template patch was first located and where this peak is, that is how you calculate the pixel offset or the displacement for that patch. Now, important thing to keep in mind is if you're using imagery that is already georeferenced, the pixels and the orientation of the step size and the search distance and the image patch size will all already roughly align with latitudes and longitudes or your preferred coordinate system. But if you're working in the range azimuth space, such as if you're doing this type of work on SLCs or RTC images, then these will be kind of strangely oriented. So at the end of the day, you might have to end up transforming the pixel offsets you calculate from the azimuth range space back into a georeference space at the end of it. And it's just kind of important to keep track of that as you go along. So this is kind of what the basics of feature tracking looks like. But as I mentioned, there's also an option to oversampling. So oversampling comes in when you kind of have coarser data. So for instance, if we were to zoom in on this peak right here and look at it, in the original image, you might see something like this, where here again, we have X and Y, and the color denotes the degree, basically the value of the normalized cross correlation, with red values indicating higher values. And if you're working with coarser data, you might end up with a scenario like this, where the results are very blocky. And it's unclear if the true peak is in the center of this pixel or slightly off to the left or right, just because the data is so coarse. So one thing that is commonly done as well is that we oversample this normalized cross correlation surface to get much finer data. And this allows us to locate this peak with a lot more precision and hopefully get a better estimate of the offsets. This is generally a good idea to do, but two things to keep aware of is, one, this will increase processing times quite a bit because you're vastly increasing the resolution of the imagery you're working with. And also, it may lead to overly specific results. You might be working with 10-meter imagery, but if you use oversampling, you might get oversampling results that say we had an offset of like 1.00076 meters in this location. And just, keep an eye on that. Even though it's giving you values that specific, that might not be the actual precision with which you're making these measurements. So that's kind of a rough overview of the parameters of feature tracking and how to make it work. I just want to show you quickly what this looks like when you perform this type of analysis. So we'll make sure that the environments work for you all later on, but for now, I'm just going to run through this analysis here, and you guys can follow along just watching with me. So the first thing we're going to do is download 2 Sentinel-2 images, which are a type of optical imagery over the Malaspina Glacier in the panhandle of Alaska. And in case, if you don't know, haven't seen this glacier before, it's pretty incredible what it looks like. It's one of the largest Piedmont glaciers in the world. Here is its source, and it's running down right here. It has this beautiful ribboning, and if you've ever, worked with like a can of paint before, it looks kind of just like that. One of the coolest natural features on the Earth, in my opinion. And we're going to use these Sentinel-2 data to actually track the movement of this glacier. So now that we've downloaded our imagery, I've created a small function here that you can check out, which is basically just a helper function to use the Autorift package. And basically, it's just changing the data from some Autorift specific names like skip sample into names that I mentioned earlier. So here we're defining our step, our minimum patch size, maximum patch size, our minimum search distance, and our maximum search distance, and whether or not we want to resample or oversample the data. So let's go ahead and run this. And then the next thing we're going to do is just load our imagery using GDAL and subset it to a specific set of bounds. And for this, we're going to be using band 8 of the Sentinel data, which I believe is near infrared, but if somebody knows better, please feel free to correct me. So if we just plot the raw data, this is what we get once it loads. So here's the Malaspina Glacier on May 12th, 2020 in Sentinel-2 imagery, and here it is in May 27th, 2020. It's pretty difficult to tell if this glacier has moved between the two. You might be able to see some of these dark patches and make some guesses about how fast this glacier is moving, but without using a tool like Autorift, it'd be much more difficult to get good measurements. So now let's take these 2 images and use them to run Autorift. So we're going to go ahead. We're going to use the defaults for all of the parameters I mentioned above, which are defined just up here in this function. And I'm just setting the step here as a reminder that, like, oh yes, we're working with a 16 pixel step. And so this cell is going to do a couple things. First, it's going to just prep all the inputs for Autorift. It's then going to transform everything into a uniform data type, just to make sure that we're all working with floats and that kind of everything is hunky-dory. And the next thing we're going to do is pre-process the data using a high-pass filter. This transforms it into the frequency space and just removes some of the high frequency noise and then transforms it back. It makes it easier for the pixel tracking to lock onto the right type of features and not just random noise. And this is probably something I'd recommend when you're processing most types of imagery. So we encountered a few errors due to some divide by zero issues, but these generally aren't a huge issue, and I run into them every time I run out Autorift. And basically this means that you'll just have a few areas of no data in the resulting imagery, but it's not too big of a deal. So now that that's done running, let's go ahead and look at some of the results. So these are the results that Autorift just produced. Here we have west to east movement, basically your DX movement between May 12th and the 27th, with the main glacier, Malaspina Glacier, being outlined about like this. And then we have the north to south movement, or basically the DY movement. Shoot, and I think this should actually be south to north movement here between the 12th and 27th. So we see the glacier is moving pretty consistently south as we go, and we have movement of up to 1,000 meters or a kilometer in these locations that we're detecting with Autorift. So, you know, in comparison to InSAR, which is, you know, typically working at the centimeter to millimeter level of detection, with this type of analysis, we can actually detect movement on the meter to kilometer scale. I think that's probably a good place to pause and ask if anybody has any questions. I haven't been monitoring the chat. Gareth or Yunjin, is there anything in particular you think would be worth addressing?
There were some questions about the difference between this and the co-registration that happens during InSAR processing.
Okay. My belief is that they're both using similar kind of offset tracking algorithms, but I believe the similarity metric they use is different. And I think AmpCore, which is the technique used inside of ISCE2, is one of the techniques that is transforming into the frequency domain first. Does that track with your understanding, Gary?
That's right, yeah.
Yeah. And so I think both work very well. I think Autorift was optimized to run a little bit faster, and so it kind of discarded the frequency domain stuff. In their paper, which I should probably have cited for you guys, I believe they compare a couple of different approaches, and they show that for this type of large scale analysis, you do get relatively similar results. Yeah, so here's the paper. I'll drop the DOI link in chat. But this is a really good paper, and it's worth looking at if you're interested in more of the details of the implementation of Autorift.
Yeah, and I would like to just add that in the implementation details, they are slightly different. In the theory, they are exactly the same.
Mm-hmm.
And in the InSAR, in the previous workflow in StreetMap app and TOPS app, we see earlier, those co-registration part, they only they do the co-registration for the two images, but they actually already correct for all the other things. So what we call the co-registration refinement, in that stage, in the co-registration, we use the amplitude cross correlation. And at that time, we only usually take just one value, such as the mean or the median of all the pixels, and use that one value for the co-registration. And that is most of the time very accurate enough.
Okay.
In this case, we are actually using these to do the measurement, so we care about the spatial variation a lot.
Yeah, in TopSap and StripMap, there's also the option to do dense offsets, which is much more similar to what Autodrift does. For the co-registration matching, we just do these measurements at widely spaced to maybe every 1,000 pixels or every 400 pixels or something to get an overall average of shift, as Junjun was explaining. But with the to actually have a map of earthquake deformation or whatever, you use dense offsets that are very similar to the Autorift. The big thing I think of Autorift is that it actually uses this multiple resolutions to get first the overall shift from the two scenes at a coarse resolution, and then it focuses in and gets a higher resolution mapping using smaller windows. So cross correlation is done by using a window of data and comparing it to the window of the other scene, and the size of that window determines the resolution of how accurately you can measure things. And Autorift uses different size windows at different stages in the processing. The AmpCore doesn't do that.
Eric's right. That's the fundamental difference between what's in the ICE software for co-registration and Autorift. It's a multi-scale thing. In Autorift, and it automatically searches for the peak as it drills down to finer scales. Whereas the other one in ICE basically does it at one scale and then that you specify, and then it oversamples the surface, the correlation surface to get the best possible estimate. There are strengths and weaknesses to both. Autorift is very fast, but it also can sometimes make errors. So that's the trade.
And one thing I know I personally encountered with Autorift is at points it will run with silent errors. So you might run all the way through and not encounter an error, but then you try and produce the image at the end and it'll just be a non-value or all NA. So certain parameters in Autorift tend to work well, but like certain combinations of chip sizes and search distances seem to have worked poorly for me in the past. So it's good to keep track of which parameterizations are working well for Autorift, because you could just run into a pairing that just doesn't seem to work for some reason. I think there was a question about an equivalent notebook or demo running Autorift on SAR image pairs. So I'll chat a little bit about that in the next section. So looking at the next section, what we're actually going to do is create a stack of these Autorift measurements to look at velocity maps using the Autorift products that are generated on demand by ASF's HYPE program. And that does use Sentinel-1 SAR data under the hood for most of its processing. And basically, the flow that the HYPE processing uses is that I believe it takes the SLC image and first turns it into a, first does co-registration between the two images using another SAR processor called Gamma that is relatively similar to ICE and what it's trying to accomplish. It co-registers, basically resamples them to get them co-registered, and then runs Autorift in the azimuth range space for these Sentinel-1 SLCs. And just to show you all what it looks like if you want to request your own Sentinel-1 Autorift pairs from ASF's HYPE program. Basically, you would go in, and if you're familiar with ASF's Vertex, which is basically our tool for finding and downloading data, you would define a polygon of interest where you would like data for, define a start date and an end date you would like for that data, and then select a file type. And right here, for now, we want to work with Sentinel-1 single complex data. And then select a scene you're interested in making image pairs with. And once you have your scene name here, you can go ahead and copy this. And I just have this another tab. From the dropdown over here, you can select different types of searches and go ahead and select an SBAS search, which stands for small baseline subsets. And I believe Yunjin will go into what that means a little bit more in the MinPy discussion tomorrow. But you can paste that into the CNAME, search for all the possible pairs that you could make with that image, and that produces this graph over here, which is a baseline graph where you have your perpendicular baseline on the y-axis and your temporal baseline on the x. By selecting one of these lines that represent an image pair, you'll highlight it in this field over here. And by clicking on these three little boxes, you can request either a interferogram of these two images, or you can request an Autorift pair. And then that'll kick things off and get things going for you from there. One thing to note is that the parameterization setup right now in this in Vertex for Autorift is specifically set up for glacier monitoring. So if you want to use this for landslides or earthquakes, I'd probably recommend running something like dense offsets inside of ICE or running Autorift externally from Vertex if you want to do those type of analyses. But for this notebook, you don't have to go through any of that. Basically, we've gone ahead and pre-baked a set of those hype InSAR or those hype Autorift products. We're just going to go ahead and download those. I believe they cover most of basically 2016 to 2020 for the Malaspina Glacier. We'll go ahead. We've downloaded those. Now we're going to extract them to the local file. Define a couple of helper functions that help us basically access the data and pull the dates from their names. And here we have all the different time periods that we have data for. So all the way through, it looks like most of 2021 with a bit of 2022 as well. We're going to go ahead and load these all using GDAL into one stack where the z-axis represents time and x and y are just the range and azimuth spacing of this data. Or I believe these have already been geocoded, so these represent latitude and longitude. We'll just take a temporal mean of this stack of data and then plot that in an interactive graph here. So here is the temporal average velocity. I believe this is in the southward direction for the Malaspina Glacier over most of 2021. When you guys have access to the correct kernel for this notebook, you'll be able to click around at different points and kind of see what's going on. These three numbers down here at the bottom represent your x coordinate, your y coordinate, just in a NumPy array space. So what is your row and what is your column? And then the number in square brackets is the actual average velocity at that location. So you see it's very low off the glacier, but then can get up to almost 3 kilometers per year on the glacier itself. So, once you can click around on this for a while, but once you have a point that you're interested in looking at the velocity history for, just have it selected on the map, run this cell down here, and it'll pull the x and y coordinate for you. And then we'll subset our time series stack there and just plot the velocity here. And I'll zoom out a little bit so you all can see this. And here we can see the trend in the velocity based on the multiple sets of Autorift images that we have for this site over from the beginning of 2021 till March of 2023 or of 2022. We see a seasonal trend going on here between the two that is pretty strong. But if we were to click up here and run these cells, we see that the velocities are a little bit lower and the seasonal effect is a little less strong. So that's kind of gives you a broad overview of what's possible with Autorift and other pixel offset tracking methodologies. You can move pretty quickly from just looking at offsets between two images to building up a long time series over time that you can then use time series tools like MinPy also to further process and get better estimates of your average velocities and other metrics like that. Just a couple important tips that I've kind of collected from my time using this is for the SAR data, remember that unless you're using the height generated Autorift products, that you are going to be computing them in the range and azimuth space. So any velocities or offsets that you create are going to be tied to that geolocation. You'll need to remember to reproject those. Not only the physical pixels, but also the velocity values they contain into a geographic coordinate space. The second bit is that the processing parameters are very important to this type of analysis. I'd really recommend varying your search window size and your chip size and your filter size to just make sure you're getting the highest quality offset maps that you can, because a lot of times defaults might not produce results that are applicable to your area of interest. And then also in general, larger window sizes tend to allow you to detect slower movement, but you do tend to lose resolution as you create larger and larger patch sizes. If you're not changing your step along with your patch size, you can kind of be fooled into thinking that you're actually getting very high resolution data, but most of those measurements are going to be correlated or dependent with each other. So just remember that as you are increasing your patch size, your effective resolution of your measurements is going down as well. And then the final section is just some broad thoughts on when should you use feature tracking and when should you avoid it. The best case scenario for feature tracking is generally when your movement is faster than the maximum detected by InSAR. This is kind of the main case where it's used and where it's most useful. One thing that's really interesting is that as imagery gets produced at higher and higher resolutions, the accuracy of this feature tracking techniques tends to be tied to the pixel size you're working with. So as we get higher resolution data to work with, and as InSAR data is starting to get higher quality, and more data is being produced at longer wavelengths like L-band, there might come a time in the future where the places where you can get validated with both these techniques could overlap, and then we could combine both these techniques together in really interesting ways. But that's a little bit off in the future for now. And then the next important caveat is that this type of technique works well when most of your movement is horizontal, but it's not going to detect basically any vertical movement at all for the most part. InSAR is much better at detecting vertical movement, and hopefully if you are more interested in vertical movement, I would try out InSAR first with the hopes that your movement is kind of in the range where InSAR is valid. And then, as I mentioned earlier, you want to really be working with high resolution imagery whenever you can that has good geolocation accuracy as well. And then feature tracking tends to be bad when either movement is very slow, or when it also tends to be bad when movement is mostly in the vertical direction when you're working with low resolution data. Another stumbling block I've run into in my own work is that feature tracking does not work well when your imagery has banding issues, because the pixel tracking algorithms will tend to lock onto the banding and find high similarities in places with similar banding. So there are techniques you can use to pre-process this data with banding issues. I'm thinking mainly of Landsat 4 and 5 and a little bit of 7, particularly where there was the scan line error. But you'll want to make sure you pre-process any of those images before running it through Autorift, because it will lock onto the banding in those images. And then the final caveat is feature tracking tends to not work well when the features you're tracking are being removed from the scene. This happens with landslides when you have a landslide that is constantly moving and the features you're tracking are falling into a river, and the river is then eroding that material. So for instance, you have a tree that's moving down the landslide and then it falls into the river and the river takes it away. Autorift isn't going to be able to detect the tree in the second image because it's been moved away by the river. So the Autorift results at the very edge of the landslide are not going to produce good results. I believe that a similar concept would probably hold for the calving fronts of glaciers, but that isn't something I've worked specifically with. But I'd just be cautious if you're working into something like that. And then, we'll work on getting the kernel working for you all, but the homework for this notebook, once we get the kernel working, is just to spend some time looking at this map, pulling out interesting points, and then looking at the trends that it produces in the time series trend in the glacier's velocity, and just take some time to look at those and look at how that is varying at different points of the glacier and see if you see any interesting trends popping up. And with that, happy to open it up to some more questions or discussion. So Bala asked an interesting question. Are there any limitations to selecting the image pair, especially related to the temporal gap? The important limitation isn't necessarily the temporal gap. It's more the amount of movement you're expecting between the two images at the site. So for instance, in some location, a glacier might be moving so fast that even images that are pretty close together in time might not work as well. But if you have a feature that's moving slowly over long periods of time, then feature tracking will still work. So it's really about that velocity. I'm less familiar with how well techniques like Autorift will work with SAR data when you're in areas with low coherence. I know it mainly works on the amplitude portion of the data, but I don't know if the signal could become difficult for Autorift to lock onto in those cases.
Yeah, for SAR data, it's similar. Like InSAR, the cross correlation also actually depends on the quality of the cross correlation, which is a function of the spatial coherence. We used a lot in InSAR. So I would expect if there's a big gap in time, your cross correlation quality will also be worse.
Okay, great. Good to know. So yeah, if you're working with very, very long time separations, maybe think about using optical data in those cases, or at least not Sentinel-1. We have another question in the chat. The estimated errors in feature tracking method due to cross correlation are much larger than InSAR techniques. Is there any way to reduce the error at Autorift? Yeah, you're right about the errors generally being higher in Autorift and other feature tracking software. This in part is due to the fact that they're set up to track much faster moving features. So the error kind of increases relatively with the speed of the motion that you're trying to detect. In terms of ways to reduce error in Autorift, I found that if you can find images that are as similar as possible other than the movement you're hoping to measure, that's the way to decrease error as much as possible. So for SAR data, like Yunjin was mentioning, that probably means selecting images with very high coherence with each other. One thing that I found useful in optical data is that if you can select images taken at the same time of year, like let's say November 2020 and December, or November 2020 and November 2021, basically a year gap, the shadows that you see on the surface tend to be aligned the same way, and the vegetation is at a similar stage of growth, and that promotes higher similarity between the images. And so I found that yearly pairs of data tends to work better for optical data. Another technique is just, really fine tuning the parameters such as the pixel size or the patch size and the search distance. And also, I believe oversampling can sometimes help to get slightly better results as well. Yeah, that's a good point. They also mentioned in the chat that this is also the same for glacier surfaces where there's meltwater present. It'll create a large error because that's a massive change in the image that isn't related to the movement you're trying to measure.
I would like to add on to your 4.6, when should we use feature tracking or speckle tracking? Another very important part is speckle tracking or feature tracking can give us a 2D measurement, while InSAR can give us only 1D. So the 2D measurement and then combining ascending and descending, this can give us sometimes a 3D deformation mapping of the surface, which is very nice and has been demonstrated through many years in the big earthquake or glacier studies.
Yes, that's a really good point. And I think that type of 3D velocity measurements have also been used to infer the slip surface of landslides underneath the Earth. I think a lot of the work at the Slumgullion landslide has worked at that with, I think Eric has done a lot of that, particularly with UIVSAR data.
Yeah, working with me.
Oh, yeah.
On Slumgullion landslide did a very dense pixel tracking with UAVSAR as 0.6 meter pixels in azimuth and 1.2 meters in range. So they're very fine pixels.
So I see a question in the chat asking, does the Autorift feature tracking provide better results than coherence tracking method in SAR data? I'm less familiar with coherence tracking. Does anybody have any thoughts on that?
The feature tracking, I believe, is similar in the SAR as the amplitude cross correlation or the incoherent cross correlation, while the coherent cross correlation takes both the amplitude and the phase data while they're calculating the correlation surface. So in theory, from a study from DLR, they showed that the coherent speckle tracking is around a square root of 2 better in terms of accuracy than the incoherent one.
That's really good to know. So the idea there would be, would you pre-filter the images to only use feature tracking on coherent pixels?
Sorry, I don't get what you mean.
Never mind. Not important. And then another question, could this method work for lava movement? I think glaciers can lose coherence similar to a lava flow. I don't know if it would work well for lava or not, because it flows very, very rapidly in a given day, but then I believe it would be new lava flowing on top. Somebody please correct me if I'm wrong about this, but I think the fact that there's a lot of new things in every images when you're working with lava flows might make it difficult for Autorift to track similarities between images.
Yeah, I don't really know neither, but I would love to see some examples. That sounds actually very interesting to see.
It'd be great to see somebody do that, and even if it's just proving that it won't work, that'd be very interesting.
I mean, there's all sorts of lavas out there, right? The very slow moving ones might be viable targets.
Mm-hmm. And I imagine you could also think of a situation where maybe you're using something like drone data or something like that, where you can get much closer temporally separated images, if they were only an hour apart. And yeah, maybe feature tracking would work well in those cases.
Well, this has been awesome. I think we can take a break.
Sounds good.
There's only one session left, and I'm leading it. Let's come back in 5 minutes. At 1:45 Pacific. Just a brief break. Hopefully, it won't take too long. The next part.
Yes.
Thanks, Forrest.
No problem.
Okay. So the last section for today is an exercise or like a demo really of a couple of ways of converting from line of sight measurements to more intuitive measurements. Of course, we've made the case several times throughout this that radar line of sight is what InSAR measurements are made in, and how the ground moves may project in maybe initially unexpected ways into the line of sight deformation that we actually measure. But if we have multiple measurements of motion from different lines of sight, then we can undo that process and actually go back to more intuitive measurements of how the ground is moving. For example, is it moving vertically? Is it moving horizontally? Is it moving east, for example, or up? We can say something about that from looking at data from multiple viewing geometries. So I have a short exercise, hopefully not a very long exercise, on how we do this. So let me get set up here. There's my browser. Turn the chat back on. Of course, yeah, feel free to keep asking questions as we go. And we'll load the notebook for this exercise. So we go to GeoSync. We go to UNAVCO 2022, and 4.4 is where we're heading to decomposition of velocities from multiple viewing geometries. And we'll do this first notebook, which is called Simple Line of Sight Decomposition Berkeley Hills. Everyone see this clearly enough? I hope that's the case. Super. So you can see what I'm doing. Okay, so this is more of a kind of a simple demonstration rather than a huge number crunching exercise. But we're going to look at some InSAR data from landslides in Berkeley, California. It's a place where I used to live. Increase once more. Sure, I can zoom in a bit. Maybe. Is that good? Are we still going to be able to see all the things? Yes. Yes. So we're going to go to Berkeley. It's a place that's on an active fault in the San Francisco Bay Area. We're actually going to process or do some time series analysis of interferograms from this area tomorrow. But today I'm just going to show you some very local and reasonably fast moving deformation features from that area, just to the northwest of the University of California's original campus. In this case, we're going to look at we're just going to have very simple calculations using line of sight vectors and range change rates. The only dependency of this whole notebook is NumPy, because we're just going to do some simple calculations, but I'm going to show you some data from these landslides. And here they are. So maybe I could stretch you a little bit. I have two data sets for this area. These are old style permanent scatter at InSAR time series, or velocities rather. They were processed by Alessandro Ferretti, who was the inventor of this method, I suppose, and his team at TRE Altamira. And there are two of them from two different viewing geometries. So this is a data set from the ERS satellites. Each dot here is a strong scatterer of radar that has high amplitude and stable phase over many years. This data set spans 8 years, from 1992 to 2000, made up of data from both ERS-1 and ERS-2. I've given you some geometric information about these SAR acquisitions. They're taken from a descending track. The heading of the satellite, so the direction it's flying, this T direction, the track direction, is 191 degrees, and its incidence is 23 degrees to the vertical. So quite steep incidence compared to Sentinel-1. And that the horizontal direction of that pointing direction is shown here with the L arrow. You can see that there are a number of points that have a different color to the data around them. Pretty much everything that's light blue is the same as the velocity at the bottom of the hill from the sort of the city of Berkeley proper. We call it stable Berkeley because we're measuring things next to with respect to that. So you can see that, you know, I've drawn perimeter lines around these points that have different velocities, and I've averaged them within these perimeters to give you the, you know, the average movement of every one of these landslides in range change rate. So they range from 12 millimeters a year, so reasonably fast, at least for the sorts of things that measure with InSAR, to maybe slower. You may also note that there is a color change as you move to the northeast through here. At least it's resolved pretty well in the descending data set. And that is because the data points on this side, in this area, are moving with respect to the data points on this side because there is a fault that runs through here, a Hayward fault, and that fault is creeping. So it's slowly moving, and you can see the sense of motion. The range increase that's going on here, the negative velocity, moving towards the satellite at a faster rate than the data on this side. So this side is moving eastwards slightly faster, and that would be consistent with a right lateral strike slip at the surface. That's not the only data set we have, though. We have radar sat data. So as Eric was saying, this is fairly rare. And definitely the complaints from the people at TRE about having to process it and trying to process it means that people don't normally try, because it's wrought with all sorts of problems, particularly bad orbits were an issue for the processing of this. But they struggled and were able to come up with something. So just drawing the same perimeters on the data, you can see now most of the area is covered by this kind of like light green color, which is around 0. But the landslides appear in a bluer color than the surrounding data points. And if you draw the same perimeters as I used before, you can see that these encapsulate most of the points that seem to be moving anomalously in this area. And the rates again vary from a few millimeters a year to 12 millimeters a year. This is an ascending data set. That's important because, you know, we need diversity of line of sight information if we were to do anything with this data. And so the difference, of course, is the satellite is flying from south to north at a heading of 348 degrees, so just slightly west of north-south, and it's looking to the right at an angle of incidence to the ground of 34 degrees. So there's our two data sets. You can compare them side by side or up and down and see that, you know, there are some interesting features here, that they are different in how they're represented in these two data sets, these two sets of land, these 5 landslides. And you can see, for example, that the sense of relative motion between the landslides and the surrounding areas is different. And does anyone know what that implies about the direction that these landslides might be moving? Anyone tell me, either in chat or out loud? Horizontal. And do you care to expand on why? Might take more than one word. Excuse me, by the way, someone is here fixing my air conditioning in my house. You may hear some background noise. It's moving away from one line of sight and moving towards the other. Yes, exactly. You have negative line of sight values, line of sight velocity or range change velocity values on one data set. So you can see here, these are all negative. And so that means that these points are moving towards the satellite in this viewing geometry. But in this one, the velocity, so negative, sorry, I'm doing this wrong. Moving away from the satellite, negatives towards. There. I'm telling myself in knots here. Yes, they're moving towards the satellite in this direction and away from the satellite in this one, which is pointing to the west. So yes, you see that they must be moving horizontally. If it was moving vertically up, should they be mostly similar? Yes, exactly. Because they are both mostly sensitive to vertical motion, because they both have steep incidence angles, which are steeper than 45 degrees, that means they're most sensitive to vertical motion. So if they both were showing the same vertical motion, you would see the colors would be the same in both data sets. Either they would be going down, which means they'd be red, or they'd be going up, which means they would be blue. And I already mentioned the abrupt change of line of sight velocity in this data set, but we don't really see it in this one. Does anyone have any idea why that might be? Layover? No, we still have points. We don't see any classic layover features in the underlying. Yeah, so parallel to trace. So the flight direction of the satellite is very, very similar to the strike of the fault. The fault's moving is oriented kind of in this kind of direction, like 315 degrees to the northwest. And the fault strike, the flight direction is close to that angle, which means that the look direction is almost perpendicular to the fault, which means it's not going to be very sensitive to movement in along fault direction. So it could well be moving. It's just that the InSAR is not very sensitive to it. Very much like how we saw yesterday morning, the north-south component of motion on the fault we were looking at, where we were making those sort of synthetic models, basically had almost no representation in the interferogram. It's a very similar situation to this, that the flight direction is such that you just aren't sensitive to motion in that particular direction. So that's the data. And what we're going to try and do is decompose the velocities that we've got, these two sets of velocity measurements in the ascending radar set data and the descending ERS data, and convert that into horizontal and vertical velocity. So a good horizontal direction to choose would be east-west, because the satellites are pointing almost due east-west in both situations. And a vertical motion obviously is intuitive as well, and both of the observations we have are going to be sensitive to it. So we have to think again about line of sight vectors. And yesterday I showed you some examples from Sentinel-1, assuming fixed lines of sight, and how you can calculate it using the angles that are provided to you in the ICE processing software. Here, we didn't use ICE to process the information. Also, it was a simpler time for InSAR in that everything was strip map imagery, and the pointing direction of the satellite radar was always 90 degrees to the heading direction of the satellite. So a lot of the early studies you'll see of this kind of thing use the heading angle as a means of calculating the pointing direction. And I'm going to run through that here because that's what I have. So there's a couple of examples of trigonometry to try and figure out how you actually convert these angles that you get, incidence and in this case heading, into X, Y, and Z components of line of sight, the line of sight vector. So here's the first picture, and this is imagine incident radar striking the ground and making an angle theta with the vertical. So that's your incidence angle. Now, if you want to convert that to the vertical component of line of sight, it's a pretty simple process. You just have to take the cosine of this angle theta, and that will be the vertical component of line of sight. Of course, there is also a horizontal component of line of sight, and that in total is given by the sine of this angle. It's the opposite side of the triangle, not the adjacent side, and that's sine theta, that length there. But of course, we know that in map view, that has to be divided into X and Y components. So if you imagine that, then here we have now the velocity of the direction of flight of the satellite, governed by this angle phi, and the direction of pointing of the satellite in the horizontal direction is given by p horizontal, ph here, hat, and that's got an a direction that's divided, that is basically given by phi plus 90, the heading plus 90 degrees. And now that could be divided again, of course, into a north component and an east component. And it's another trigonometric thing that you would do. You can turn this into a right angle triangle by drawing a line across here with a right angle there. And anyway, if you do that, then the east component, the direction, the component in this direction is given by the sine of this angle phi plus 90. And the north component is given by the cosine of that angle. So you multiply that by what we know about the total horizontal, which is sine theta. You get something that is sine theta times sine phi plus 90, and that gives you the x component, and the y component is sine theta times the cosine of phi plus 90. And if you like to play around with trigonometric identities, sine phi plus 90 is the same as cosine theta, and cosine phi plus 90 is the same as minus sine theta. And so in the end, you get this expression for the line of sight vector in terms of the heading angle and the pointing direction as follows here. And we use the negative sign for the vertical because the radar is pointing downwards. So it's in the opposite direction to up. And that's why you get a negative sign for the z component. So we can then do this. We can actually go in and calculate these components. So what you'll see is, I think when I typed in the numbers the first time round, I typed them in for the wrong data sets. So here's a little wrinkle for you. You have to go back and check what numbers you should put where. So the ascending data has a heading of 348 and an incidence of 34 degrees, and make sure that those are the numbers that appear in this cell, so you can type them in here. So it's the azimuth, the heading, angle. We're going to convert our degrees into radians at this point because Python does all of its trigonometry in radians, so we need to use radians. And you can do the same for the incidence angle, and then you can execute this code cell, and then the one beneath will give us our line of sight vector. So you can see that it's got a reasonably large x component, a small y component, and a big negative z component. And that is, in my mind, the right set of numbers, because we know that the line of sight angle is pointing at a very sort of mostly east-west direction, and it's pointing down steeply. So you should expect a positive x component, a negative vertical component, and a very small positive y component. And that indeed is what we get. So you can do the same for the ERS data, the descending data set, to make sure that the right numbers are in here. 191 degrees for the heading direction and 23 degrees for the incidence. This evaluates all those sines and cosines and puts them together in an array. And when we look at the contents of that array, what do we get? We get a negative x component that is moderately sized. You get a very small north component that is positive, and a very large negative vertical component. Again, it's pointing west, down, and very, very slightly north. And that is in keeping with what we should expect. So, you know, I included some tips on sanity checks here, because you should see these kinds of numbers for satellites with these kinds of incidences. You can check whether the relative sizes of horizontal and vertical components are consistent with the incidence angles. Remember, there should be bias towards vertical because these are steeper than 45-degree incidence. So you should expect to see the vertical component have a larger amplitude than the horizontal. only in among the current satellites, I think, when you're in the very far subswaths, do you see anything where the horizontal components could be larger than the vertical. So like the very far range of Sentinel-1 has an instance of about 46 degrees. And in that case, you would expect, you know, the horizontal component to be very slightly larger than the vertical. There's a question here. The velocity is in the line of sight direction, consists both of horizontal and vertical components. Can we confirm the velocity is exactly one direction by looking at the line of sight velocity? Not on its own, no. I mean, if you have a mental model or like a working hypothesis of what the motion should be, then you can maybe make an assumption that you see what you're seeing is in a particular direction. If you have some understanding of the process, for example, if you're seeing sagging of the surface before a sinkhole forms, then you can assume probably that most of the motion is down, vertically down, and then you can interpret your data in that way. But yeah, you can't do it without making an assumption of the direction of motion, basically. What we're showing you here, you can at least constrain two components of motion because we have two measurements. We have two lines of sight and two independent measurements of movement. So in theory, we could solve for two different components of velocity. And that's what we're trying to do here. Okay, so that was my first sanity check, was are the relative sizes of the horizontal and vertical motions, you know, in keeping with the incidence that we're getting. Next, are the signs of the east components consistent with the directions that the satellites are pointing? I think so. The ascending data was pointing, had a positive east component here. And the descending component, the descending data had a negative east component. So ascending positive east, yeah, okay, that's good. And descending positive west, or negative east, positive west. So negative east component for that one, that's also correct. Great. And third, are the north components consistent with a polar orbiting satellite? Which means, are the north components very small? And yes, they are. They're much smaller than either of the other two. So for ERS, the descending data is less than 0.1, and for the ascending data, it's very slightly higher than 0.1. But yeah, they are the smallest components, and that is consistent with a polar orbiting satellite flying more or less north-south. Cool. So does that make sense to everyone so far? Because now we can move on to how we actually turn this into how we try to solve for these two components of motion. Okay, so it's an inversion. It's an inverse process that we have to use to convert from two measurements in line of sight to horizontal and vertical, to east and vertical in this case. So we have two observations, and we can solve for two motions in two directions. And whoops, and because we're doing InSAR, and because they're polar orbits, it makes most sense to look at the vertical and east-west directions. Those are the two things that these satellites are sensitive to, or most sensitive to. And what we want to obtain then is a pair of numbers, the horizontal velocity and the vertical velocity. And we can write that as a vector. So MH and MB in a column vector. And I've written it here transposed so I could put it on one line. And we want to use, and we also have two measurements of range change velocity are for range change rate, ascending and descending. We can write a vector of those as well. And we can relate range change velocities to these decomposed velocities by this equation. Basically, R or R prime equals some matrix P times the vector M. And this matrix P must contain some of this line of sight information that tries to relate the horizontal velocity to the range change rate. So what we do then is we can think about what goes in here. Basically, we have a row of ascending line of sight information and a row of descending line of sight information. And because we're only concerned with the the east and the vertical components of velocity, we just use those components in this matrix. So this ascending horizontal component is basically the east component of the ascending line of sight, and this ascending vertical component here is the vertical component of the ascending line of sight vector, and same goes for descending. So we can write these 4 numbers into this matrix because we've already calculated what they are up here. And because this matrix problem is a well-posed problem, 2 inputs, 2 outputs, we can do a very simple matrix math to solve it. It's one of these standard forms of problem. Just go through, pre-multiply by the transpose of P, take the inverse of P transpose times P and pre-multiply it with that. And at the end, you get M in terms of the inverse of PTP, P transpose P times P transpose times R. And these are all things that we know. So we can just evaluate for M by basically adding the values that we know to P and multiplying them by these things. Easy. Technically, it's easy. It's easy because computers can do matrix inversions for you, so you don't have to figure them out by yourself. So here it just is assembling the matrix P from the ascending and descending parts of this line of sight vector, and then you stick them together, and what have you got? You've got the matrix P. So it's got some east components and some vertical components in it, and the signs are still the same, and everything works. And then all that we have left to do is to actually evaluate this for every landslide. And because we can do this all in one go, I just made arrays that contained the line of sight velocities, the range change rates for the 2 data sets, the ascending and descending data sets. You can compare these numbers 12, 2.7, 5.3, 5, 12 with these. They look the same. Okay, and the other one probably is 2. 7.2 minus 4.3 minus 7.6 minus 2.8 minus 12. Yep. Brilliant. So all we do is we calculate the PTP inverse, because we use it a bunch of times, so why not calculate it now? So there's a function in NumPy that does an inversion of a matrix, and we multiply P by its own transpose here and invert that and store that at that value, at that variable. And then we just loop through all of the lines of sight. We grab the values for the ascending and descending for each one in turn. We make a little vector R out of that. And then we do the matrix multiplication, and we print out what we get for the two numbers. I guess I'm calling it U. I should change that to M. It'll print out the first and second number, and you'll get the velocities. Okay, done. So fast. So as we would expect, perhaps these landslides are moving mostly horizontally at rates that go up to quite fast, up to 25 millimeters a year. And you can see that and the directions of this motion are all negative, so they're all moving to the west. And the vertical velocities, with one minor exception, are all negative as well, suggesting the landslides are moving down, down and west. That is very much in keeping with what I know about this area. These are the Berkeley Hills. You're going uphill to the right, which means these landslides moving negatively to the west, negative to the east, so moving to the west and moving down are sliding downhill. You might quibble a little that one of the numbers that we get out is negative, is positive in vertical, but it's very, very close to 0. And I didn't include this, but if you were to do some kind of error analysis, almost certainly this could be moving downhill with an error, and you wouldn't be able, it's not so very anomalous. that rate, you're getting there. So that's how you do it. That's how you convert from two lines of sight measurements into horizontal and vertical motion. And you can do fancier things when you're calculating your P matrix. For example, you can project your velocities into a particular horizontal direction if you want to. This is useful if you're trying to measure, for example, the direction in the movement in the strike direction of a fault. If you had something like fault creep, so if we, instead of trying to model the landslides, we were trying to model the rate of creep on here, then you might want to project them into the strike direction, which is 45 degrees west of north here. So there are fancier things you can do, and you can refer to a couple of my papers on that if you're interested. I can give you pointers later on places where I've done this. I also included a couple of a few different examples, like the ERS data was published in Science by George Hilly and Roland Bergman some time ago, talking about the dynamics of these landslides. It's actually really interesting. They moved faster during a wet winter than they did on average. I think Eric already mentioned in passing earlier that one thing that may happen is that the fluid could percolate through the landslide to the basal shearing zone and actually lubricate the movement of the flight or increase the pore pressure, or the rain could actually just soak into the ground and make the ground heavier and more likely, and less likely to resist motion. Either way, there was something interesting going on with those landslides. I've also linked a kind of classic paper by Tim Wright, which described various ways of trying to do this with multiple lines of sight, and the conclusion was that you need a long track information to be able to resolve north-south motions. But he had a really interesting data set with multiple different incidence angles, but the different incidences wasn't enough to be able to pull apart the north component of motion. And one example of the paper on the BAM earthquake that Eric and I are both authors of, that shows that if you use image offsets as your long track information, in this case azimuth offsets from SAR image matching, what Forrest was just talking about, basically, then you can actually get this full three-dimensional displacement field, which is cool. So that's one notebook, and I have a second one. But before I get to that, has anyone got any questions?
I should also mention, while we're talking about those Berkeley Hills landslides, that since 2009, I've been having NASA collect UAV-SAR data with 3 different angles across those landslides, so we can measure the full three-dimensional motion on those landslides by using the same calculations. But because with UAV-SAR we can define the flight line directions, and we have flight lines that are parallel to the fault and other flight lines that are perpendicular, and so we actually have at least 3 different direction measurements on those landslides all the time since 2009 using the UAV-SAR data. And we've been doing that at many other landslide locations, including Slumgullion in Colorado and the Eel River landslides in Northern California, where we also get actually 4 different look directions to much better constrain not just 2 components, but all 3 components by having 4 different measurements.
I also
3 or 4 different measurements.
I forgot to mention one other thing. So I started looking at these landslides when I was working in Berkeley. I actually lived in the Berkeley Hills. My house was located like here, the core of the fastest moving landslide. My garage door didn't shut properly. And my landlord was trying to sell the house for most of the time I was living there and was unable to find a buyer. He ended up evicting me so he could move back in himself. So there you go, InSAR. And it shows actually that there's actually some internal deformation to this landslide. The core of it is moving faster than the edges. So I just averaged all the velocities in here, but we're actually going a bit faster even than that. crazy. Right, so I have another notebook. And because yes, you can do all this manually and you can make these vectors yourself and you can invert them yourself and so on, but you might want to do this in a more sort of automatic and programmatic way. So I'm just going to show a demo of a notebook I wrote that does the decomposition for 2 Sentinel-1 data sets that I processed from ARIA standard products using MintPy, because I was interested in looking at the COSO geothermal field, which is just north of where we had an earthquake in California in 2019 near Ridgecrest. Eric already showed the Ridgecrest earthquake interferograms a few times. They're really pretty. But COSO is this little weird sort of volcanic complex just a little bit further along strike from where the Ridgecrest earthquake ended. It had some weird behavior actually during the period around the time of the Ridgecrest earthquake. It had very few aftershocks in that area. That was kind of odd. There were lots of aftershocks of the earthquake to the northwest and to the southeast, but not in this zone where the geothermal activity was. Anyway, so I processed it because you can do that using ARIA standard products. You can basically on a whim decide, I want to look at this geothermal field, and within like half a day, you have basically everything done. You have all the velocities that you need, you have the time series, you have everything. So anyway, I was curious how much vertical and horizontal motion there was in this area, so I wrote a notebook, and I'm sharing it with you now, that just takes the outputs of MintPy, which you'll meet tomorrow in detail, and figures out what the decomposed velocities are. So this has more, I think, more things as inputs. It imports NumPy and some math and matplotlib for plotting, but also GDAL to put things in, and it also imports MintPy as a library. So MintPy can read MintPy format files, so that's good. There's a function that just allows you to pick numbers out of an array that we use later on. And here's another place where I messed up. I may have messed up the version that you're reading, the path to the files that you need to read. So if you run this and it crashes, then you need to check where the data actually are. In here, in this data directory, I have 2 data sets. One's ascending track 64 and descending track 71. Both of them contain a folder called MintPy. It contains a file called velocity.h5 and then an input thing, and another HDF5 file that contains the geometry information. So all of this is very much the way that it gets produced during when you're doing when you're running MintPy. So anyway, there it all is. Make sure this path goes to data, and then the descending track and MintPy, and that will give you the directory of the descending data, and the ascending data is there. We'll crop this data file to a certain area, and we will use standard MintPy file names for the velocity and the geometry files. And you click this thing, it reads it in. Nice. And you can use matplotlib to plot those just to see what you get. So you have descending velocities in meters per year plotted here, big negative, MintPy and ARIA tools, ARIA tool specific, ARIA standard products. They use ground displacement convention, where up is vertically up, or positive is vertically up, and negative is vertically down. So in this case, we see subsidence mostly, or movement away from the satellite anyway, and maybe 2 centers of it, two dark blue blobs. And in the ascending data, you see something quite similar. You see again a dark blue blob and maybe a second dark blue blob. There are some differences to the further field motions, but both show about a centimeter plus per year of range increase or vertical ground negative ground displacement. So there you go. There's our data. What we're going to do is then we'll pick a fixed point to reference everything to. I can't remember what it is. There is a point I chose. Looking in Google Earth, I found, I think, a rocky hill that looked pretty stable, and I said, okay, I want the coordinates of that point, and we'll make that be 0 in both data sets. So I'll subtract the velocity of that point from all the others. And that's just so that they have a common reference when you're comparing the velocities. So all this is doing is finding the velocity of that point, or the location of that that long point in the data set, and subtracting the velocity at that point from the data. Okay, done. And so next, what we're going to do is go through and compute for every pixel. Now, we just did it for five landslides with average velocities before, but this time we're going to go through every single pixel that these two images have in common and do the same decomposition calculation that we just did pretty manually in the previous notebook. I have a place where you can specify your sign convention. So we're using ground displacement sign convention here, some -1. When you run it, it tells you that. We'll make some places to put velocities and velocity errors. We'll loop through every row and every column of the image. And all we do really is calculate the line of sight vectors for those two data sets using the exact pointing azimuth and the exact incidence angle for each pixel. I'm not assuming that it's constant now. I'm actually using the values that MinPy has. And we make a little 2x2 matrix, just like we did. Is our little design matrix. We'll invert it and we'll output the results. So you run that, and because these computers are fast, that doesn't take very long at all. It's amazing. And then we can plot the answer, what we get. That seems to take a little bit longer than the. Oh no, it's still running. Okay, I spoke too soon. So it's chugging through, but it didn't take very long, and now it's plotted it, and this is what you see. So this is really cool. Most of the motion, as you can see, again, 1.2 centimeters a year of vertical movement down. One big subsiding area and one slightly smaller one. Okay, that's kind of in keeping with what you could have inferred from looking at those two velocity data sets in the first place. But what I think is interesting is the east component here. If you look, there's two blobs. One's yellow and one's blue. So one's positive east displacement and the other one's negative east displacement. So this one is moving to the east. And this area is moving to the west. So they are converging with each other, I suppose. And you can see that this area of subsidence fits pretty nicely, snugly within those two blobs. Imagine this thing here could fit in there. So what I think is going on is, this is an area where people are pumping steam out of the ground to make geothermal power. It's actually owned by the Navy, and the Navy, US Navy in this part of the world is a power utility. They're making electricity. You're pumping steam out of the ground. Of course, that means the ground has less volume, so it's going to compact. But also, it's actually pulling in the sides of the edges of the reservoir inwards. The ground is contracting inwards as you suck more steam out of the ground. So that's an interesting signal of horizontal contraction and vertical subsidence that you see at COSO. And for your edification, in case you ever wondered how once you've done some of these operations on a file, how you actually go about saving it as a format that you can use. So I noticed this morning that we showed you how to subtract a ionosphere correction out of an interferogram, but we didn't actually show you how to export that interferogram as a file. It turns out it's pretty straightforward. You just there's a bunch of GDAL functions that will do that. I decided here to save it as a GeoTIFF, but you can go to the GDAL website and find there are a load of codes that you can use for other file formats. It's a complicated set of things because you want to make sure it has all the spatial reference information that you need to actually make a file properly geocoded. But that's all here. You could probably repurpose these code snippets for other things. You want to save out some files, and there's a few little foibles like you have to flush the cache, otherwise it doesn't write the file. But if you run this anyway, it will save two files in your space here, east-west velocity file and a vertical velocity file. And actually in the inversion I did, I also calculated the uncertainties. I haven't saved them, but you could also edit this and output the uncertainties of the velocities that you're just estimating. That's my demo on how to do image decomposition. I'm happy to take any questions on this. Hopefully this is a very useful set of skills that you'll pick up, because people like to think of things in terms of coordinate directions that they understand. How fast is it sinking? How fast is it moving west or east? And this is sort of analysis that we very often do. Questions? Any thoughts? Fears? Concerns? Is everyone just exhausted? Sympathize? Are the geo files from MintPy similar to those from ICE? They have four layers, I think. Yunjin can confirm it. They contain the XML files. I don't think so. MintPy uses as its internal format HDF5. It's slightly different from ICE format in various things.
Well, when you load the ICE output into MintPy, it's getting all the information. It's just putting it in a different format.
Yeah, I mean, the first sort of section of this notebook is just me unpacking HDF5 format into a bunch of NumPy arrays that I can do math on. Tomorrow, of course, we'll show you how to make those HDF5 files by running MintPy, which will be exciting. If you get really excited, and you can make an ascending data set to go with the descending one that you're going to make tomorrow, then you could try and do this kind of decomposition with your own files, which would also be fun for anyone who's feeling particularly enthusiastic. And also, I think has one issue might be that the number of ARIA standard product downloads that you can make now is so large that you might actually run out of 200 gigs of disk space if you try and do everything all at once. I don't know. We'll see what happens.
Yeah, I think there's some places here in California where if you just download all the possible interferogram pairs, you'll get over 200.
2000.
Or yeah, and each one is only about 50 or 60 megabytes, but if you make hundreds of them, it adds up quickly.
Well, if there aren't any questions, I can step back here. Oh no, I do need to share my screen again because we have homework. Hopefully not too strenuous. Let me see. Let's go back here. Okay, so we made it. Oh, I want to point out in the syllabus now I've started putting the links to the live sessions in here, so you can go back and watch what we covered yesterday. That's up there. The high definition versions take a lot longer to process, but they will appear at the same links in due course. So today we don't have a video yet because we haven't finished yet, but by tomorrow morning we will be able to post that video. So as for homeworks for today, hopefully they're straightforward. One is to complete the ionosphere removal notebook. And also, second homework is to complete the Autorift notebook. Remember, there were some questions embedded in there at the end that Forrest showed us, I think. So go off and do that.
For extra credit, people can do an ionosphere correction on some other pair.
That's right. try tops into tops ionosphere correction, maybe if you're feeling particularly. So people ran into errors. Was it because you didn't change the path to the files in the right places? It could have been. I can't see these PDFs. Yeah, it looks like you might not be finding the file. Yeah, I think that probably is the problem. If Python can't find the file, then it throws up a really complicated long message. gtip export doesn't appear to be working for me. Okay, we can maybe look at that later. It should. I mean, well, I have this. It made a file for me 6 minutes ago. You might be able to open it. Oh, there's nothing there? Interesting. Well, I can. Let's see. It works on my home machine, on my office machine, I should say. I have not verified, I guess, that it works here. So let's see, gears of 4.4. $580 K, so it didn't do nothing. Interesting. I have QGIS installed on here, but if one does, in theory, you could open these, download them. Yeah, I have to be in my office where I have QGIS, but just because it doesn't open in the browser or like your image viewer, it doesn't mean it won't work in a proper GIS package. So that would be my advice. Try it there. Because yeah, I thought I'd done it wrong too. Then I opened it in QGIS, like, oh, see the same pattern. Okay, so we know what our homework is. Maybe someone will let us know on Slack if indeed these files do open like they're supposed to in a GIS package.
If you open it with like the Mac preview program or some other image viewing program, it might think it knows how to read that geotiff, but not really know how to deal with the scaling issues.
Yeah. It's not going to render nicely into like RGB color, almost certainly. If that's all we have, I think we can call it a day. Tomorrow is Mint Pie Day. So, oh, we have a confirmation that it opens in QGIS. That's cool. Does it show like a good pattern of ups and downs and left and right? Great. That's all that really matters. You can pretty it up once you can open it in something that actually can understand what it is you're opening. Fantastic. Thanks everyone for coming today. Have a good rest of your day or start of your day or whatever. We'll see you here tomorrow, 10 a.m. Pacific. And we have office hours tonight if anyone wants to go over these things in a bit more detail or has questions or problems that we haven't been able to solve.
5 p.m. Pacific.
5 p.m. Pacific in 2.5 hours or so. See ya.